So, welcome now officially. I'm glad to have so many people in the auditorium today with us. Welcome to the 6 Viennese talks on networks and resilience, the principles for resetting a post-corona world. Again, it's great that we have you with us. My name is Valerie Streibel. I'm working at FS Research, and we're hosting this event together with the IASA Institute. I am here in charge of operations and corporate communications, and I will be the technical / cooperation guide through the whole 4 hours that we have together today. A few remarks before I hand over to Brian Fath. That there is a chat function that you already obviously saw and posted in. You can use this or the Q&A section in the screen below you for the Q&A session later on. The questions, as I said, will be part of the panel discussion. So you have 2 sessions, and in the beginning, the keynote speech. Brian will actually talk more about the agenda in a bit. I think that's about it. The webinar will be recorded and then posted on the IASA website and also the FS Research website to actually check it out later. But of course, I think you're used now to the webinar section. None of you will actually be visible in the video. So it's just the panelists that will be shown. So there is no GDPR problems on this in this context. Yes, that's about it. I'm handing over to Brian now for guiding you through the agenda. Brian, the floor is yours.
Hello, good evening, good afternoon, good morning. Welcome, thank you for joining us today, whichever time zone you're in. I think based on what we've seen in the chat, we can safely say at least all 3 of those apply. I hope you've been safe this past year, and I hope you have access to the vaccine soon if you haven't already. As Valerie mentioned, my name is Brian Fath. I am actually a professor at Towson University in Baltimore, Maryland, but I also have a position as a research scholar at the International Institute for Applied Systems Analysis in Vienna. The Viennese Talks in Networks and Resilience was born out of a collaboration between Harold Katzmeyer and myself and FAS Research and IASA over a dozen years ago. Our first workshop was held in 2010, and Buzz Holling was our keynote speaker at that time. Since then, we've tried to have sessions about every other year. In fact, our last one had been planned for March of 2020, and we were hanging on right to the last minute to see if that was possible. And of course, in the end, that wasn't so. We put things on hold, as everybody has. Who knows when we can meet live again. But we thought to take advantage of the virtual setting and have a session that otherwise probably wouldn't have been able to come together due to some travel issues, right? So we're here today to talk about systems ecology and ecological principles, but how they can help us to build back better after COVID. So the speakers were all humble systems ecologists, mostly drawn from co-authors of this book that came out last year, A New Ecology Systems Perspective. We also have a strong belief that principles from ecology can teach us a lot about how we can better manage socioeconomic systems. And so that will be one of the themes that is running throughout the session. So as Valerie also mentioned with the format, we have a keynote address that we'll start with Ika Darnhofer is providing. And then we will have 2 sessions, each with 4 short talks and then time for discussion afterwards. And and then a short break.
Thank you very much, Brian. I'm happy to introduce our first speaker, Ika Darnhofer. Some of you may know her. She's an associate professor at the Institute of Agriculture and Forestry Economics at the University of Natural Resources and Applied Life Sciences in Vienna. And her research focuses on management and decision-making on family farms. And just to give a quick overview, I think that's exactly what she's going to talk to us today about, that the transformability aspect of resilience. To add something else, she's a member of the executive committee of the International Farming Systems Association, as well as a member of the editorial board of the Journal of Rural Studies. Thank you, Ika. The floor is yours.
Thank you very much. I'm very, very honored to have been invited as a keynote speaker, as a social scientist, just before all these eminent ecologists. And I kind of feel a bit like the warm-up band before the big concerts. So here you go. I've been invited to talk, and I'm trying to put my background, which is social science, farmer decision-making, resilience of family farms, into the topic of today's talks, which is sort of the post-corona world and resilience thinking and what that can help us go forward. I will focus on the transformability aspect of resilience, which I believe has not received its due attention, let's put it this way. And maybe Corona can help us really move towards more transformative thinking. So resilience thinking, just a little primer for all of you, is fundamentally about learning to live with change. Change in the system itself, in the context, in the feedback, in the dynamics, all of that is very dynamic, and we tend to underestimate the dynamics. And I do think, and I will present that a bit later, that Corona gives us a great example and illustration about how dynamic and uncertain our world actually is. And the question then is, in resilience thinking, how does a system, in my case, it's usually farms, deal with all that ongoing change that is highly uncertain? Well, first of all, obviously, we can buffer things. Essentially, there's a drought. We don't do much. Right now, we have frost in Vienna, which is rather nasty because it's going to kill all the beautiful flowers we have, and we might not have an apricot harvest this year. Probably you just don't do much. You just persist and change and hope next year there won't be a frost at that time. You can also adapt. That's usually understood as incremental adjustments. So small adjustments, changes, but essentially you maintain the system, the system on the current pathway. And different to that and distinct from that is transformation, which is really about creating a fundamentally new system. And that's challenging because fundamentally new is usually something we do not know much about. And usually humans are not very keen on doing something entirely different they know nothing about. Well, this looks very different. Adaptation and transformation in practice is actually quite difficult to make a difference because adaptation, lots of adaptation can add up to being transformative. They can, but they don't have to. So they're still quite distinct. Now, the problem is that the transformation, that third strategy here, has been a bit sidelined. And the question is sort of why? Partly it's probably linked to the fact that resilience thinking started in ecology. And in ecology, transformation is usually seen as undesirable. So we don't really like atrophicated lakes. We think that that flipping is not a good idea. We'd rather have the clear state rather than the turbid one. There have been other studies about farmers extracting too much water and the problem that came with irrigation, and that can also flip and transform ecosystems. So generally the idea has been to try to identify tipping points so they can be avoided. So we don't try to get there. Resilience root is thus in conservation ecology, which was the initial name of the journal. Now it's called Ecology and Society. So this is just an illustration that the aim is generally to preserve the ecosystem in the current state, or if possible, to improve it. If your humans have already degraded it somehow, to try to get it back to that system. So again, it's all that bouncing back issue. And there's very little emphasis on transformation. So conceptually it's there. It's always mentioned in the definitions by various members of the Resilience Alliance, but it's not really something that's emphasized where there's a lot of work on. Social ecological systems is what we look at, and we understand them as deeply and intricately linked. And the dynamics are fundamentally driven by these interactions, by the interaction of the natural and social systems. They're still seen as distinct. So here we have an ecological system and a social system, which have their own little dynamics, and the ecosystem has its own little dynamics, and then they interact. So this is sort of how they've been conceptualized. And these dynamics tend to be fairly complex and adaptive, as in they change, complex as in they're not really predictable. And as I mentioned, I'd like to use the current pandemic just as an illustration to understand what a CAS is, because sometimes it's a bit difficult for us to understand, because world usually before Corona seemed quite predictable by and large. We had a few larger crises, but essentially we kept on pretty much the same. One feature of a CAS is uncertainty and the unknown, and that's very different from risk. It's really that we just don't know. At the beginning, a year ago, none of us really understood how it would spread, what the incidence rates is, all this vocabulary that we learned lately, who is most affected, how that has changed. We used to have other groups in society, globally quite different. The vaccine development, initially it's like, oh, it takes years to develop a vaccine. Actually, it was a lot faster. Then production was actually the problem. Maybe it wasn't entirely production, now distribution is a problem. There were quite a few surprises. There's a lockdown. I did hear about the lockdown in China in December and January, and I was sure this would never happen in Europe. There is just no way you're going to have a lockdown in Europe. Well, surprise, it does happen. I'm old enough to know that we used to have borders in Europe, and we used to have passport checks at the borders. And then came the EU, so Austria joined the EU in 1995. That's a long time ago. I never thought that we'd again see border controls within Europe. So this is just a good example of seeing how it can be very surprising, very fast, very radical. And it's also been seen as an example how all the national governments have been seen as not being able to do much because, globalization, we can't do anything. And suddenly the national governments remember that they can do actually quite a lot. This is just as a reminder that they can if they want to. The question is, when do they want to do something really radical? Currently, we have a lot of emergence, also a feature of a CAS, and that's variants. So now in Europe, we're battling the British variant, but then we have all sorts of mutations that come our way and immune escape, and we don't really know how these will interact with various vaccines. So that's going to be interesting. Children's mental health problems are a big issue. How about schooling? Something that we did not discuss a year ago. We have all sorts of anti-corona demonstration, also something we didn't quite expect coming. I mean, we are rational people, so things will be explained to us, and obviously we will do what is rational, which means do whatever the government tells us to do because they have actually listened to scientists, right? Right. Also these sort of societal dynamic that we didn't see coming, and essentially none of us really knows where we're going to be in 2 months. We hope that with the vaccine things will get back to normal, but will it? And the long-term impact is something we've been discussing quite little because the current depth that the governments are going into is going to massively limit what it can do afterwards. So again, this is just an illustration of what it is and how this is really a social ecological dynamic. Because the COVID virus itself is not the problem. The problem is how it interacts with our current society and the structure of our, the processes and values that we have in our society. So imagine COVID-19 in the medieval times. Obviously, the impact would have been very, very different. And therefore, it's really the interaction between nature, in that case, the virus, and how a society is structured, and that is structured based on certain values that we have. We want to travel globally, and we can. We have a lot of mobility going on. We have urbanization, and the design of our cities makes a lot. We have growth-oriented economies that are very important, and therefore, we destroy forests. And the biodiversity loss definitely seems to contribute to these kind of pandemics that virologists tell us will become more frequent. And underneath all of that, there is also an assumption of rational choice. The model is called truth speaks to power. So a natural scientist, in that case, virologist, epidemiologist, essentially devise information and give that objective knowledge to policymakers, and they then make reasonable measurements and measures. And we now find out that that doesn't work that way, because actually there's a lot of interest groups that try to interfere with that, and how much governments can and will actually listen to scientists is diverse and open to interpretation. And there, so back to the science, we tend to have a lot of disciplinary sciences, and there is in that case very little integration of, for example, epidemiology, political sciences, and sociology, which would have allowed us to understand the whole dynamics a lot better, but currently we don't, because all of these disciplines are rather siloed. So back to our social ecological system, the question is, they're very dynamic, they're surprising, they can change radically in a short amount of time. We see that. Corona has shown us that. Now, the question for resilience thinking is, can we explore that beyond buffering and adaptation and use the principle of resilience thinking to really push towards a transformation? Because I would argue that business as usual is not really something we can go on. Nor do I think that a little adaptation, that is marginal changes, tweaking here and there, is going to be sufficient. The crisis that we as a society, as a global societies are facing is climate emergency. We produce plenty of food. How come we still have so many that go hungry? We have a biodiversity loss that is really problematic. We have poverty, income inequality, gender inequality, all problems that we know, that we have a lot of data on. Surprisingly little changes. So there's a lot of proposal by scientists how things could change, but very little changes. We have marginal changes, but they don't actually do much. The climate crisis is not really moved away since the Paris Agreement or since Kyoto. Really changes are marginal. And now the question is really, can we essentially go towards transformation? So really what we should do is work towards transforming the social system while maintaining the ecological system. And that is now very tricky because we just saw that these kind of interact, and the question is, how do we conceptualize that? And it does ask us to think in radically new system, not just a bit of tinkering here and a bit more there and a bit less there. We've been trying that for decades. It has not made a big dent. So if we want a different post-corona world, radical change, transformative change is what we will really need. And that means new ways of thinking, new ways of doing, new ways of being. And that does include research, science, the whole research world, us. We are part of the social system. And I do think that each one of us, it is kind of helpful if we ask ourselves, how do we contribute to maintaining the status quo or to change it? And these are our practices as scientists every single day. What do we count as knowledge? Who or what do we include in our research? Who or what do we exclude? How do we communicate? To whom? All these are questions. And the question is, can we change them? Can we change our foundational assumptions? And that means transforming science, because I do not think that we can keep science the same and expect society to transform. And just we tell them how to do all different, but we do not change. I'm not so sure that more of the same is really going to do what we need if we are going to contribute to transforming our society. And here I'm just giving you an example that's one of several where we can say, okay, this is a group within the social sciences that's trying to really ask the hard questions about really thinking differently. It's called the ontological term, and I think it's understood a bit differently than in ecology, but essentially it's about questioning the fundamental assumptions of modernity. And that's everything that comes with 18th century Enlightenment, that's Europe here, and the Cartesian sciences, which are rationalistic, objectivist, mechanistic. So we can characterize them that way. There are other words we could use, but essentially you get the image. And essentially this ontological term questions all of this hierarchy, which are linked to dualities, culture, nature, human, non-human, subject, object. These are strong differences that have been made by René Descartes, but all those that came afterwards. So there's us human and there's everything else. Many do believe that exactly this difference between nature and culture, between society and ecosystem, this conceptual difference that we make contributes to how our Western world deals with nature, which is rather exploitative. We also make a strong difference between reason and emotion, mind and body. And the question is, are we truly just cognition? Is our work really just intellectual? Because I'm rather passionate at what I do, and that's an emotion. And sometimes I feel something's off. There's something missing. There's something there. That is an intuition, and it is not rational. And what does that mean if we actually reclaim our humanness as researcher? And how do we define science versus belief? So everything we do according to Western norms of science is scientific, everything else is belief. Maybe there's other forms of knowledge that we should also acknowledge. It does not devalue what we do as scientists, but it means that we should integrate and see others as equally valid because they add certain aspects. And essentially, there is a work towards understanding the world in a non-dualist and relational way. And that has profound implications for us as scientists, because then these are not anymore two separate bubbles that then interact. They're deeply entangled. And essentially, it devalues everything that we tend to do, which is making the God trick. That's the disembodied gaze from outer space, where we see things in a non-emotional, objective way, which is usually what we see ourselves as scientists. Now, the question is, how creative are we to think this differently? Can we imagine ways to do research so as to actually contribute to society's transformation? And chances are we will need to transform science if we are to contribute to that transformation. And that is my last slide. Do we truly want to bounce back after COVID? I will argue, no. I would like to bounce forward different. Thank you very much.
I think, Ika, that also the auditorium would applaud if we would hear them. Thank you very much for the great presentation. I actually had already, we will have time for a few questions now. And if it's okay, I'm just gonna tell you the question. It was, like the person said, I'm curious to see how opportunistic anti-globalists will be as pandemic has driven this fear.
How opportunistic?
How opportunistic
yes.
Anti-globalists?
There are many tendencies, and the question is, what can we do to essentially counter these strategies? Again, I am saying, I see many opportunistic, populist grouping here in Austria using it for their own good and against the global good. I think we have to be very careful. But the question is, what kind of science do we need to do? What kind of information? How do we interact with the public if we actually want to contribute to saying we need a different world and a radically different world?
Thank you. I would hand over now to Ursula Schaller to the next, that will present the next session to you and the great panelists we have in store for you.
Thank you, Valerie. I'm very excited to be here and having been asked to chair this first session that includes 4 speakers. The people in these sessions today have been colleagues of mine and mentors, so it's really exciting to be part of it. We will have the 4 talks first, and then we'll have a question and answer session at the end of the 4 talks, where we have about 30 minutes. So if you have questions, please post them either in the Q&A or in the chat. And if you have a question for a specific person, then just please state so in your question, because then we can direct it more. Otherwise, the question will be asked to all the panelists of the first session. So I'll introduce the first speaker, Brian Fath. He already introduced himself at the beginning, but he is a professor at Towson University in Baltimore and a senior research scholar at IASA, the International Institute for Applied Systems Analysis near Vienna in Austria. He is an expert on systems ecology, urban metabolism, and sustainability. And today we'll hear from Professor Fath on ecological principles and network mutualisms. And the floor is yours. So I should probably rather say the screen is yours, since we don't have floors these days. Thanks, Brian.
Okay, thank you, Ursula. Ika, you had it wrong. That was a very hard act to follow. So you put me in the difficult position. The beautiful figures, as always, the hand-drawn figures, I love those. So I'll have to ask you to get some of those. I also agree completely with the need to transform science itself, a whole nother passion of mine. But today I'm going to talk about one of the other things you touched on, which is the non-dualist and relational aspects of complex adaptive systems, and in particular in the context of network mutualism. And make sure I can move ahead. One quick advertisement before I jump into it is that one of the things that IASA does every year is holding a Young Scientist Summer Program, which is for PhD students to come to IASA for the summer for 3 months and work with IASA scientists on research projects. And so obviously for 2021, it's settled, but the application deadline is always going to be kind of mid-January. So you can look for that at the IASA website. And we're hoping that 2022 will be in person. 2020 was virtual and 2021 is also virtual, but should still be a great summer for us. A little history. There was the first edition of New Ecology System Perspective was spearheaded by our colleague Sven Jorgensen, and he hosted a workshop for about a week. He invited us all to the island of Mern in Denmark. And that's a photo there on the cover of the book from Mern. And the book then came out a few years later in 2007. In the interim, he was also spearheading an effort to do some other work in terms of limits to growth, but looking at nature and how that helps to understand how we can actually flourish within limits to growth. And he had already worked out an effort to have a second edition of the New Ecology book. But then unfortunately he passed in March of 2016. But we were able to use that momentum and to keep going. And we actually met, I believe it was January of 2017 at IASA for another brainstorming session. So we decided to put IASA on the cover of the new edition. And yes, and so we're fortunate that we had lost two of the authors of those books, Sven and Enzo, but the rest of the authors are actually all speakers here today. So we were able to pull that together. One of the things that came out of that book was, during our brainstorming, was this idea of really trying to synthesize what is it that ecosystems do. And I understand there's all sorts of problems with lists, and you know, you always exclude something or maybe have redundancies and so on. But after several decades of really thinking about this, we came up with what we think are 9 principles that define pretty well what ecosystems are doing. And so that's the foundation for all of this. And the first ones are the material constraints, which are the real fundamental, you know, first and second laws of thermodynamics and the periodic table. Basically, you have to obey those things. Those are the material constraints. Nature does, and does a good job with that. The next two are the ontological properties that we observe, and that's the fact that ecosystems are able to use energy to move further away from thermodynamic equilibrium, right? So they're able to complexify themselves. And we look at this as the physically driven biological aspect, because it's something biology does, but it does it strictly physically in some sense. Bob will probably correct me on that in a second. But the second part is that they not only move further from equilibrium, but they co-evolve and adapt while they're doing it, right? So they have that resilience feature already built in. So that's the biologically driven biological aspect. And those two together, I think, actually teach you a lot about you know, understanding ecology and understanding nature. And then from there are the phenomenological properties, which are the fact that ecosystems are highly diverse. Again, the complexity issue coming in terms of different types and numbers of types. They also work together in networks, and we see networks everywhere in nature. There are also hierarchies that emerge as a natural order of those organizations. And then lastly, that there's a large amount of information at the genetic level, at the biochemical level, and even at the process level. So all of these together, we think, could be the foundations for a new ecology, for an ecology textbook, and that's what we tried to do in writing that book. What I'm going to focus on today is number 7, which is the ecosystems work together in networks. That's my own kind of passion, again, I guess I would say, and how we can apply these to other kinds of systems, not just ecosystems, but socioeconomic systems. Well, networks are everywhere. We see networks in all kinds of applications. It helps you to represent the system as interacting components. You can identify and quantify direct and indirect effects in the system. And what I'm actually going to do now is to go through a little bit of the nitty-gritty of the details of how we can see some of these properties. So I'm going to get a little bit technical here for a second, but here's an example of one of these ecological network models. This is an oyster reef model. It's almost the Drosophila of ecological network analysis, because it's used so much to test the kinds of ideas that we have. It was empirically derived from work that Damon Patton had published back in 1981. And it basically shows the flows of energy, the exchanges of energy between the different compartments in the model. Maybe it's a little more easy to see the pictures of them rather than just the names. So we have oysters at the base of this food web. Well, there are no plants in this one, but that's for its own reasons. I don't want to get into it. We'll take what we have. There's detritus, there's predators, and then there's bottom feeders, and they're all exchanging energy according to what was observed out in that reef system. Well, one of the things that you can do immediately is to understand the connections better is to construct an adjacency matrix, which is essentially a binary representation of the ones and zeros of either is there zero if there's no link, one if there is a link. This particular network has 12 internal flows, so there are 12 non-zero elements, and each one of those is in the place that represents the flow from one compartment to another. When you have an adjacency matrix, then you can take powers of that adjacency matrix, and that actually tells you the number of pathways that is commensurate with the power of that matrix. So it's one of these very useful properties of networks and matrix multiplication that you see here. If you have a two-step, A squared, it tells you all the two-step pathways, the number of paths between any two nodes that take 2 steps, or that take 3 steps, or 4 steps, or 5 steps, and so on. And you see that the numbers are rising much faster than the power, such that if you even get to something like 10 steps, you have now hundreds of different pathways of flow. And if you get up to 20 steps, you now have in some cases millions of different pathways, unique pathways of flow between any two nodes. So immediately that just kind of blows your mind, because it's saying there's so much going on there in the structure of that network that we just wouldn't see otherwise, right? That this is kind of revealing all those possible pathways for energy and influence to travel in that network. Well, that's fine, and that does tell you something about it, but it's also useful to know something about the actual flows in the network, because in this particular case, we know not only that there's a connection between any two compartments, but we know the amount of energy that's flowing between them. So we have something called a flow analysis, which allows us to quantify what the flow is between any two compartments of any length of that of pathways. So what I've drawn here is the representation of that 6-compartment system, but only with the first order paths. So the filter feeders, these oysters here, are giving flow to the predators, and they're giving flow to the detritus. That's it. That's their only direct connection, right? They have no direct connection with the other 3 compartments. And in fact, what this number represents is essentially the fraction of flow, or the probability of flow, that flow going through this oyster reef compartment is going to make it to this compartment. So about 38% goes there, only about 1% goes to the predators. The rest is lost from the system as heat loss, or as metabolic waste, or even just downstream waste. But then if you look at the second order pathways, you see more of the compartments emerge. In fact, now compartment 6 disappears. There's no way to get to the predators in 2 steps. There was in 1, and there will be in higher ones, but not in 2 steps. But this is representing the flow that goes from the filter feeders to the other compartments in 2 steps, to the other compartments in 3 steps, other compartments in 4 steps. And you can continue to play this game, of course, indefinitely. But there's another nice trick in the network analysis toolbox, which is that you can actually sum up this infinite series. As you were to continue to take out those powers, they will eventually go to 0, so that you can add up all the terms. And there's a nice shorthand in order to do that, which we get then something called an integral matrix, which is the sum of all the powers of that first flow matrix that we had. And this particular representation is now showing you what that integral flows are. Now, these are no longer probabilities, because this is a sum of all the flows along all possible lengths. So it's telling you the impact that the first compartment has on every other compartment across all the lengths of the indirect flows. And then one of the things that is another interesting thing to take then is to look at, well, what was the relation of those indirect pathways, the ones 2 and greater, versus the direct pathways? Because we know the direct pathways. That's what our data set gave us. That's what we're measuring. It turns out in that particular example was that the total flow, this is non-dimensionalized, so these are just the sum of those past matrices I showed you, was 8.3, whereas the direct flow was only about 3.3. So 5 units of the total flow came from indirect flows. So more of the flow is coming from the indirect pathways than the direct pathways. So as a field ecologist, and you're making observations, you need to do that in order to get your data sets. but then recognize that there's all those other things that you're not seeing that are part of the actual contribution to the functioning of that system. So when the indirect effects are greater than the direct, this leads to one of the key results of this entire theory, which we refer to as either dominance of indirectness, or I believe in the book we use network non-locality as a way to describe that the network allows you to see the importance of the non-local or non-adjacent parts of that system. So again, we have unexpected behavior that's emerging from these system interactions. Well, we can do with the network, it's always bidirectional with our flows. And so although flow is going out from one compartment to another, it's always coming into the compartment. And so you get a completely different perspective if you now do an input analysis, where you're saying, what is the flow that is coming into each compartment, right? So from the predator's point of view, they're getting almost 70% of all their flow from the oysters, even though it was only 1% of the flow out of the oysters to the predators. So we're now taking it not where my flow is going, but where is my flow coming from, right? So this is this bidirectional analysis that we can do. And the detritus was getting about 75% of its flow in the direct direct step from the oysters. Again, you can do the power series to see the indirect flows. So you can take g squared for 2 steps and g cubed for 3 steps and 4 steps. And again, the indirect pathways continue, but again, they are dissipating down to 0 over the long term. So you can sum up this infinite series and get the integral influence that each one has. And now something interesting comes from the input analysis here, was that each compartment actually has a value exactly equal to 1. What that says is that, and it's a product of this particular network, because there's only flow into the oysters as the source of energy for the system. So indirectly, every compartment is entirely dependent on the oysters for their energy, which makes sense. So without the oysters, they're all going to perish. They don't have any flow sustaining them. So in this particular case, all flow is dependent on one supplying source. If you had a different network, you'd see different numbers, but you can still then tease apart where that is coming from. All right, so when Ika mentioned about relational aspects of that, so what I've been looking at so far and showing you is what you get from the flows, from the material transactions that goes on there. But there's also relations that exist between all of those different nodes in that system. And we can think of relations as the power, the sign combination of the interaction. So you can either have mutualisms plus plus, predations plus minus, competition minus minus, and so on. It's this the two signs paired together. And there's a way, again, using the network toolbox in order to get at this more technically. I won't go through the numbers technically for this part of it, but just to give you an example, that if you were to look at a simple food chain with only 2 compartments and had corn and mice, so the mice are eating the corn, and you'd say, well, that's clearly predation. The mice are gaining energy, the corn are being consumed by the mice. If you had another food chain and you said, well, the mice are being eaten by the cats, and so that's also predation. You've got the mice are disappearing and the cats are getting fat. And if that was the boundary conditions of your study, you would think that there's 2 predation relations, and it's pretty cruel world out there. But all you had to do was link them together in a slightly more complex model with 3 compartments and put the corn, mice, and cats all together. And you see that even though, so this is your sign relations here, the plus minus shows the mice are eating the corn, and the plus minus here shows the cats are eating the mice, but the 0, 0 across the diagonal shows you that you've got the corn and the cats are not directly touching each other. However, what you see is that in indirect sense, when you run this power series out to include all the indirect pathways, that in fact the corn and the cats are indirect mutualists. So you're getting a behavior that you wouldn't have seen if you have too simplified of a model and if you don't look at the indirect interactions there. And this particular example is easy enough to walk through because it's showing you the the enemy of my enemy is my friend. I see that my time is up. I was going to show you. Give me just 2 more minutes. That the system that actually has the most mutualism is in fact an infinite cycle. All the compartments are actually mutualistic with each other, except for the one that they're passing their flow onto. So when we talk about circular economy and we talk about you know, adding more symbiosis and circularity. That's the benefits that we can see coming from this as well too. I'll skip this example because time is out. It was just back to the oyster reef again. I wanted to give you one quick hit of how this applies to social economic examples and some of the papers that we published recently using network analysis to look at global crude oil trade, urban metabolism, and US grain trade. Now the nodes are represented in these nice circle diagrams. And then with some studies we've been doing with urban metabolism and looking at carbon emissions in Beijing over a series of years. And again, we can now stack up what the different indirect flows are from the different sectors that are exchanging flows, and seeing that manufacturing and transport and electricity display are the large ones. So we had a series of years there for Beijing and how it changed, particularly with the Olympics coming. This is all work that will be published soon, hopefully. And then, yeah, so just to give some conclusions, was that all the compartments we see are connected through these indirect interactions. The indirect flows can be greater than the direct flows. The system level relations can be different from the direct observed relations. So those mutualisms can emerge from neutralisms or even from predations. And usually what we've found is that mutualism is the most dominant relationship type in the ecosystems that we've looked at. So it's a different perspective than the red and tooth and claw that we have come to believe. But the systems approach shows you that there's a lot of indirect mutualism, particularly if there's more cycling. Okay. Sorry for being a few minutes over. I hope Ursula remembers that picture there. So, okay, I will hand it back over. Apologies for being a minute over.
Thank you very much. Good to see something from the continent. So thanks for illustrating to us how complex the systems really are, something that Ika has already alluded to. And when we really paint them out, we see how many different connections are involved. Now I invite our next speaker. And our next speaker is Prof. Bernie Patton. He undoubtedly had a very large influence on the field of systems ecology. He's Professor Emeritus at the Odum School of Ecology at the University of Georgia in Athens, which is in Georgia, which is undoubtedly the most confusing address we have this afternoon. His research interests concentrate on ecological networks theory, and today he will talk to us on network synergism, ecology, the environment, and the economy. Thank you, Bernie. The floor is yours.
Thank you. It's the earliest morning address that you have, actually. And I'm working on the sunlight coming in my window here. So, new science. Yes, we have a new world in front of us and a lot of new science to keep on creating. And it's happening, isn't it? Right before our very eyes. We are moving into a new world, and irreversibility says we'll never come back. This talk is, as all my talks, overly long, and so someone will have to cut me off probably with more than 1 minute left, or even 5 minutes left. Network synergism, ecology's invisible hand. We're turning to physics first to see how physics sees reality and how that compares with how we see it as empirical scientists, as ecologists and others, economists, sociologists. Two phases, objective phases in reality, particles and fields. Each generates the other in a kind of a repeating fashion. Different kinds of one create within and across scales of hierarchical organization. So particle clusters create fields, field clusters create particles, and so forth. And that is an image then, or a concept that we're deeply embroiled in. Only we see the particles, that is the material, the accumulations as the material, concrete aspects of reality. And the particles are local, material, and concrete. They're studied by empirical description and experiment, but the fields are non-local, to use the word Brian introduced, non-locality. They're immaterial. They're distributed. I look out my window at the ecosystem out there, a forest ecosystem, and I see the ecosystem, but I don't see the networks. So there's the implicate, ontic and non-ontic parts. And I'm using David Bohm's terminology, explicate and implicate, to distinguish these two categories of reality. Ecological knowledge itself is subjective, focuses on describing material reality. So there's a third category of reality, the category brought to reality by organisms conceptualizing reality. 8.7 million of us as species are creating representations of the real reality and responding, acting in accordance with those representations. What we call holoecology, holistic ecology, is endeavoring to add a field theory, a field perspective, a real field perspective to our theory of how nature works at our levels of organization. To better implement the particle field duality that physics works so hard to introduce at the particle and subatomic levels of the organization of matter and energy. So we work within a framework we call, it's an environmental system theory of environs, and its associated analytical methodology, NEA, network environment analysis, underlie both. Environs are particle generated and particle generating fields. Well, let's take a look at this construction we call environs. There you have a model, not unlike the model, the oyster model that Brian showed. This one is abstract. It's got some notations associated with it. And if you start with the three blue inputs there, each of those is delivering something to that system. And that something we're maintaining is maintaining its identity in the system in terms of where it came from. Its historical identity is carried with it from wherever it was in the universe prior to entering that system. And so the forward analysis we do in environment methodology is exactly that. We start with the boundary relationship, and then we go forward from that and reconstruct whatever it is you want to know about the system, the dynamics, the behavior, the structure, the nature of the organization, and so on. Reciprocally, we can start at the outputs and ask, how did those outputs get to where they could be generated by the system? So we can trace back by the same methodology, but in the reverse temporal direction, to the origins as inputs. So each of those six structures there, we maintain is a definable structure, an environment, and they are, as a matter of fact, the environments of the component parts of the defined system. So you can see that. The other part of it, this is all epistemology. This is all epistemic. But we have both concrete and field elements, particle and field elements in those diagrams. So our standard, I've got 5 minutes spent or left? Left?
Left.
Spent. Thank you. Okay, well, that's helpful. Let me see. So there's a quick look at the mathematics. I'm not going to dwell on it, just to show you that it is there, and focus on particular matrices. Brian already called our attention to these adjacency matrices down here, and gave a sense of how we use those. We have two areas of network environment analysis. One has this field perspective, epistemic, implicate, if you will, carrying the field idea into it, the particle perspective in storage analysis. So we actually, for a long time, have been working in these two domains if we choose to look at it that way. And if we choose to look at it that way, then we're beginning to create a different vision of what the ecosystem is looking like and what it is to us. For example, I perturb an ecosystem and I do an environmental impact assessment of that system. And in our example, we can express those impacts in terms of the changes in the environs of each and every compartment in a model we would make of the system, right? But the different perspective here now is the environment is being impacted, yes, but I like to say that since we're perturbing the environs, we are actually deforming the field that is making up those environments. And that's a different concept, isn't it? Deformation of an extant way of behaving that is not materialistic in the system is a different concept from environmental impact assessment. So, and you can imagine then all the changes that would begin to follow on such a concept. I'm deforming what's out there into something else out there, and so on. The ABCs of NEA, Network Environment Analysis. Just quickly, I'll just go through to put some, to just demonstrate the 4 kinds of analyses we work within. One is the pathways themselves. Brian showed how to count pathways by multiplying adjacency matrices, so that is shown there. Then there's a counterpart for that for the implicate through flow analyses, a power series of matrices that converges to an integral matrix that tells us something about the flows occurring in the system. The materialistic analysis, that counterpart is in storage analysis. Again, another matrix is constructed and the power series run down to a convergent, if it convergence, concluding matrix. And then utility analysis, the measure of benefits and costs, which is a little more, a little less materialistic, isn't it? It's very definitely a relational and, in our case, an epistemic kind of construct. And there are both flow and storage, material and immaterial aspects to the utility analysis. So it's a complex set of mathematical operation that we apply to complex systems. So getting ready to, so we start our analyses at the boundary, we have the direct influences next, and then we have the whole set of indirect influences, all right? And I am now 1 minute, I've only spent 1 minute?
Unfortunately not.
Okay, so I'm going to show both directions, and let me just continue to move on to what I call the Janus Hypothesis. And I'll talk quickly through this. First, the conjectures, the Janus conjectures. We begin with what we call an aggregation nexus. Aggregation, moving away from thermodynamic equilibrium, as Brian talked about. So aggregation as opposed to degradation. And the 3 elements of that are ABCs, and they are autonomous systems like ourselves, all organisms, biodiversity, a long list of those, and then connecting them together. Then we have, we want to maximize the total system through flow, total system storage for each of these 2 phases of reality. Maximize the synergism, because that's the dominance of benefits over costs and so forth. And finally, maximize fitness of both organisms and environments. And it's that sequence which accounts for what we're tending to call or trying to investigate as our modern day invisible hand, but now finding origins in ecology. Let me not do the theorem, although I would like to, because we have some nice mathematical proofs already of the network synergism idea, that one of which is Brian's, the very first one that done in the end of the last century. Just to give you an idea though of how compartments and flows, when you couple them together and increase their diversity, will affect I just want to continue here, will affect the results. So here's that sequence, the number of compartments, the number of links between those compartments increasing monotonically, the total system through flow being generated. You can see that that is increasing monotonically, network synergism being generated. All right, so you get the idea, diversity and connectivity and the list itself, all these things are involved. And then actual food webs, this is Oksana Buzahan's 31 pastoral food webs in Ukraine that go from low to high numbers of compartments in the model, from low to high numbers of links, from low to high numbers of total system through flow, and finally from low to high numbers of network synergism. So you can see again, these same ingredients, autonomy, biodiversity, and connectivity are operating together to generate these properties, these superimposed properties. Let me do the hypothesis then, and give me two minutes to come through this, and then I'll cut off the rest. So we begin with the second law, and everything in the system is moving against that. Everything biological in the system is combating the second law. So it's anti-entropic. And here's your ABCs, the three categories of the aggregation matrix. Generating in the upper part of the diagram, adjacent transactions. In the lower part of the diagram, non-adjacent relations. Adjacent effects, then the direct, immediate causal actions. In the lower part of the diagram, non-adjacent effects, indirect, ultimate, maximizing the goal functions, maximizing storage, maximizing through flow. Again, this paired, the duality of the two phases are operating here. Then in the upper part of the diagram, we have this natural selection nexus, known to all of us biologists, exactly what that is. In the lower part of the diagram, a network synergism nexus, which is operating, we're suggesting, at the same level that natural, and with the same ingredients that natural selection is. And by the way, when I'm sorting the diagram into upper and lower halves, it's really combined, and they're being artificially pulled apart for purposes of seeing. So we get explicit fitness in the upper part of the diagram, implicate fitness generated in the lower part of the diagram, degradation of environment in the upper part of the diagram, but enhancement of environment in the lower part of the diagram. All right. So the upper part of the diagram is your explicit order, your ontic part of empirical science. What I'm referring to here as the Gaia sphere, Gaia hypothesis, basically deals with that. And in the lower part of the diagram, the implicate part, what I'm referring to as the Janus sphere. So there are the two phases of nature captured in this scheme. And then finally, the observers are there, Janus, him or herself, epistemic explicate on the one hand, and epistemic implicate on the other hand. Thank you very much. Okay.
Thank you very much, Bernie. And thank you. Unfortunately, we couldn't hear your entire talk. I see you had many more slides, but thank you for drawing our attention to the different perspectives we can have to look at a system. This brings us to our next speaker, Bob Ulanowitz. He's Professor Emeritus at the Center of Environmental Science of the University of Maryland and Courtesy Professor at the Arthur R. Marshall Center of the University of Florida. He's an expert in networks and sustainability and has expanded the field of ecological network analysis from ecosystems towards the economics, something we repeatedly hear about today. And in his talk today, he will tell us what it takes for systems to persist. Thanks, Bob. The floor is yours.
Thank you, Ursula. Es ist herrlich schön, wiedermals in Wien zu sein, obwohl nur virtuell. Anyway, the book that we're promoting is entitled A New Ecology, and is in contrast to what I would call an old ecology that was centered predominantly about the metaphor of the ecosystem as machine, driven ultimately by the laws of physics. Those laws, however, have limits that are rarely mentioned, but it's been known now for well over a century that all four force laws of physics are reversible and require dependent variables that are wholly homogeneous, so that every token is identical to all others. For example, all electrons are interchangeable, all mass is indistinguishable. If the types of a system, however, if the types of a system are few, this obstacle can be overcome by applying the laws separately to each type and then tying them together by weaving their boundary conditions together. But real ecosystems are rarely ever so simple. And the boundary value problem is soon overwhelmed by the combinatorics that characterize even systems of moderate dimensionality. You've seen an example of that with what Brian showed you. The number of combinations among n types typically scales as n factorial, so that a system with 75 species will have on the order of 10 to the 106th power combinations. That's 1 with 106 zeros after it, an enormous number. Physicists estimate that the entire universe consists of around 10 to the 81st elementary particles like quarks or bosons, and has existed now for 10 to the 25th nanoseconds, so that the potential combinations of 75 species becomes hyper-astronomical. It becomes greater than all the simple events that could have occurred all throughout the universe since the beginning, the Big Bang. And it remains beyond the ability of even the fastest computers yet to be developed. There exists another problem with physical laws. They pertain to timeless objects. Life is not an object, but a process, a temporal series of irreversible transformations that is dimensionally incongruous with the timeless laws of physics. How then to develop a different quantitative portrait of the complex theater of living ecosystems? One possibility that we're discussing today is to depict the numerous species as nodes of a network, which are connected by directed processes, such as flows of material exchanges between the nodes. The network is weighted according to the rates of transfers, yielding what is known as a weighted digraph. Okay, each arrow has a direction and a weight. From this point on, one conducts a phenomenological analysis of the topology and weights of the connecting processes. What does this mean? It means that one makes no a priori assumptions about relational mechanisms. Rather, as in engineering practice, one can proceed in black box fashion to search for quantitative formulae that combine the data into indexes that characterize the behavior of the system as a whole. In other words, this is data-driven. We're looking at what the data is telling us. Now, ecosystem networks of processes are usually replete with many internal cycles. You've seen that before, some of which may act in autocatalytic fashion. An autocatalytic cycle is one in which each member of the cycle enhances the next one. Such a positive reward loop will always favor contingent changes that increase autocatalytic action and decrement those changes that diminish local catalysis. This is the CAS that Frau Dr. Ika talked about earlier. Autocatalysis thereby exerts selection pressure on all of its components. It also exerts selection pressure on all the limiting inputs to the systems, incorporating those contingencies that augment the capture of resources by each and any species, a phenomenon I have called centripetality. And it's one that is exhibited by all living systems, but you never see it on anyone's list of the attributes of life. And incidentally, this drives the system further away. Centripetality drives the system further away from equilibrium. There was a question about that. Such autocatalytic development eventually would lead to domination of the system by a very few of the most efficient pathways, making the system vulnerable to major disturbance along any of these primary routes. To avoid such catastrophe, insurance, so to speak, the system persists by trading off some system efficiency to make room for complementary parallel flows that can assume some of the functioning of the impaired primary channels, albeit at lower efficiency. Total system activity is measured by the total system's throughput, or TST, which is simply the sum of all the internal transfers and exchanges with the external world. The nodes can be numbered from 1 to n, and the inputs to the system are considered all to flow from virtual node 0, while exports from the system are designated to flow to some outside sink n+1. Then, if Tij designates the flow from compartment I to another, any compartment I to another node j, the aggregate of all the activities becomes, as you see, the sum of all the Tij. We now invoke a definition from information theory to calculate the diversity of all the flows in terms of the Shannon-Wiener formula. Okay, all this is H equals minus summation Pi log Pi that you're all familiar with. Only here we're using the joint probability Tij over Tst of the flow Tij. Information theory, here's the neat trick, allows one to partition this diversity into two non-negative compartments. Call it A and Phi, where A is called the average mutual information in the network, or how much on the average the flows are constrained by one another in organized, efficient manner. It's an informational homologue of the conventional correlation coefficient. The residual Phi, it's called the conditional entropy, measures how much on average the flows remain independent of one another, mostly via redundancy. In terms of the Tij, these components are shown on the slide. Now it's a messy looking algebra, but notice that only things there are the Tijs, okay? There's nothing else assumed. This is something that we can observe. They are all data driven. The components can be normalized by H to yield the fractions of activity that are involved in organized efficient transfers versus independent redundant pathways. And in particular, we're going to call little a, or you call A over H, the coefficient of order. Now, this exercise can be expressed as follows. You give me the topology instance of any weighted digraph of an ecosystem or a social system, and I will return to you two positive numbers, two positive fractions that add up to 1. The first component quantifies the fraction of system activity that is constrained by the interrelation among the elements. The remaining fraction measures the activity that is uncorrelated, free of constraints by any other relationship. When the values of little a were calculated for a number of arbitrary and diverse types of ecosystems, a surprising pattern emerged. They all tended to cluster around a value of about 40% organization or efficiency. In this graph, the ordinate is sustainability. It's equal to S sustainability is equal to minus A, the order times log A, which is the product of an organization A and a Boltzmann-like factor minus log A, which maps uniformly into phi over H. In other words, it's how much slop you have in the system to be clear about it. Hence, the cluster groups near the maximum of the product of adaptation and adaptability, i.e. the potential to evolve. In order to evolve, you have to have order, but you also have to have flexibility. A common mantra of optimization is that processes evolve to maximize efficiency. We see with ecosystems that too much efficiency can be counterproductive. Sustainability in complex systems can instead become a trade-off between efficiency and reliability. Now, in a sense, this has been known for a long while. For example, don't put all your eggs into one basket. But what this exercise has shown is that the dialectic between efficiency and reliability, Bernie's Janus effect, can be quantified, and such quantification yields useful possibilities, namely formulae that provide a way to manage an arbitrary flow network so as to draw it closer to the most sustainable balance between order and reliability, what I have called the window of vitality. To accomplish this, one can invoke simple calculus by taking the partial derivatives of the sustainability S with respect to each Tij and setting them all equal to 0, okay? That would be the maximum. The exercise reveals how much each Tij needs to be changed in order to bring the system closer to balance. If you do this, if you take the partial derivatives, you get, you know, these complicated algebraic expressions, all of which involve only the Tij. But it can be accomplished in very primitive fashion. You start out with a network, you calculate the derivatives, and each derivative will tell you whether you have to increase or decrease it and by what relative amount. So you do that by a fraction, and then you reiterate, and you keep on doing this, and the system gradually approaches the balance. And that this phenomenology can be pursued entirely without assumptions on mechanisms or laws, except for the conservation of matter, I guess. The benefits of such optimization to ecosystems management should be immediately evident. But the applicability of the method to design systems, anthropological systems, is currently being explored by engineers who are now seeking to design fail-soft distribution systems. That is, systems such as supply chains that are designed with maximal profit efficiency as a goal. So finely tuned and efficiency have these chains become that many failed badly at the beginning of the ongoing virus epidemic. Our refrigerator broke down then, and we couldn't get another refrigerator because the supply chain had failed us. Now, engineers are adapting the mathematics shown here to effect a biomimicry of ecosystems that will mitigate systems failures. Papers have recently appeared that apply such biomimicry to design more sustainable power grids, water distribution systems, and traffic patterns. Now, and then I'll end on a note that perhaps the most important application of ecosystem sustainability pertains to economic theory, where efficiency of the marketplace is a sanctified goal, not to be touched, not to be impaired by conventional economics. Renegade economists such as Bernard Lettier, however, have pointed to economists' preoccupation with efficient markets as the cause behind enormous asymmetry in the distribution of wealth, as well as the frequent boom-bust cycles in the global economy. About 20 years ago, he recommended the creation of alternative or redundant currencies to mitigate such undesirable outcomes. Of course, ecologists have long recognized the unsustainability of laissez-faire economics and its deleterious impacts on the natural world. Now, we at least have begun to formulate trade-offs that mimic natural systems and can point us in a direction towards a sustainable, vital future for humanity. I thank you all very kindly.
Thank you very much, Bob. Also for picking up again that theme of transformation that Ika had brought out in her talk right in the beginning. Thank you very much. And I would like to introduce now our final speaker for this first session. I welcome Felix Miller, who until recently led the Department of Ecosystem Management at the Institute for Natural Resource Conservation of Kiel University in Germany. His work concentrates on using ecosystem modeling and holistic approaches for the management of human environmental systems. And today he will talk on the themes of ecosystem services, ecosystem integrity, and the resilience and adaptability of ecosystems. Thanks, Felix. The floor is yours.
You're still on mute, though.
Now it should be working.
Yes, perfect.
Yeah, being aware that such things can happen and that one might be late in a presentation, I thought I could this time start with the answer in the beginning. So the question was, is most always best? And the unexpected answer is, well, it depends on the subject, of course, and on the question, most of what. And one outcome will be tentatively, mostly, this is not the case. And during the next, hopefully 15 minutes, I would like to discuss the question why. And I would like to start doing this with some starting point. One of them is our new ecology book, and things I will be telling are somehow related to the 8th chapter of it. And during this book, or in this book, we have been very strongly working on the ideas of growth and development in ecology. And there are similar ideas about growth and development in economy. And the question is, how are these different ideas related? This would be the second starting point. The third one is that I'm a happy guy. I have been visitor to these Vienna talks several times before, and I have given reports on resilience of ecosystem and landscapes and floods, and we were comparing international long-term ecological research projects, and we were discussing different crazy forms of the adaptive cycle from the Resilient Alliance. The fourth point is that I want to make some very simple definitions about ecosystem integrity, which is the self-organization capacity of an ecosystem. When we talk about ecosystem condition, we think of the ability to provide ecosystem services, and they are the natural contributions to human welfare. And I would like to start the hunting of an answer to this crazy question with the practical example. We will be going to northern Germany, to the Bornhövel Lakes once more, where we have been indicating ecosystem integrity by some Oriental-based indicators. And here we can see the beech forest, which you can see here, and the values are set as 100%. And we will compare it with the neighboring maize field, which has been a forest 100 years ago. So what we see is the outcome of 100 years of agriculture. And we will not only look at the integrity, but also at the services. And there we have the provisioning, some cultural and some regulating services. And now the calculations and measurements have shown that the maize field has a high exergy capture, but many of the other items are low. And here we can see the figure of the ecosystem services, and you can see there's a lot of food production. So what has been going on here is an optimization into one direction, and therefore all the other indicators, all the other values have become small. And knowing this, we can ask, what do you think is most always best? We can continue and look a little bit at our theoretical ideas in this book. Imagine there's an ecosystem developing in a natural fashion towards a state of wilderness, then this system would follow simple thermodynamic rules. And what we observe very often is such a dynamics. Here we have the developmental state. Here we have an so-called orienter variable. And this variable is steadily rising towards a certain attractor state or a goal function where we have a lot of different components, different interrelations, nonlinear interrelations where the connectance is increasing the network cohesion and the overall complexity of the system as well. So we can say orienters are indicators of ecological systems which are regularly optimized throughout undisturbed environmental development. So are these parts of the lazy 8 figure from the Resilience Alliance. Now, therefore, they of course are related to growth and development processes, growth mainly reflecting quantities, development qualities. And there's always the question, and it still is there, does this high complexity also mean you have a high security or a high stability? Again, the question is most always best. And what I have learned in my ecology studies was that this has such a wonderful mutual elasticity, this spider web, that we can take it as a paragon for system stability, but we did not look at these suspensions right here. So if you take them also into account, it doesn't look so stable anymore. So our orienters are related with some developmental gains like diversity, heterogeneity, complexity, but there are also many costs like respiration, and we are losing flexibility and things like viability. This has been realized by Tainter as well for human systems, and he has listed a lot of benefits which we have from complexity, and during the growth, the oriented dynamics, this complexity and the benefits of it are steadily rising until a certain point when they move down again. And in this downward movement, we can see that there are maintenance costs which are growing enormously in complex systems. The flexibility is reduced. And in the end, we come back to what Bob Ulanovitz has been showing us before, to his window of vitality. And the question is whether there is a similarity between these approaches from the human environmental systems and our ecological ones. What we can say in any way is that high complexity can be related with high risks of losing network cohesion. And once again, we must say, well, most complexity must not always be the best. We once more come back to these orienter ideas when the system is regularly moving towards a certain attractor state, which in former times was understood as the final stage of ecosystem development. Now we have to say that this maturity is correlated with risk. And here we have all the orienter functions which are derived from network and information theory from thermodynamics. And here we have a list of respective risks. I know that you cannot see it, but you can download this table maybe and take a look at it afterwards. So we can summarize and say there is a strong reduction of flexibility and adaptability. So some people are talking about overconnectedness, and in these orienter stages, there is quite a big risk for a certain breakdown. Once again, mostly the highest is not the best. Now we come to ecosystem services, which are no orienters. They are totally anthropocentric, only related to human well-being and They are matters of management in the ecosystems. Nevertheless, we can try to bring them in contact with our orienter theory and say that the orienter grow. We have said this before. One of them might be biodiversity, another one might be integrity. And here we can say that the regulating ecosystem services behave similar to that. But if we look at the provisioning services, they are high in young stages and they are getting low in older stages. And the cultural services also have a behavior which gives them a peak near the end, but not in the total end of the story. And if we have a disturbance, you could see, then we are having retrogressional dynamics. We are moving backwards. This means there's no free lunch. So all positions, for example, this agro-ecosystem here, have advantages, but they also have disadvantages. It's the same concerning our national park over there. That means land users really must decide which options they want to optimize. And by concentrating on one target only, you have to be aware that all the others are lost. Here you have only production and all the rest shows very, very small values. And the highest flexibility and viability could be somewhere in the middle. So this is a point which has been discussed with our colleague Larry Lee very often. Once again, do you think most is the best? It's not quite clear, but mostly not. And if we once more take a look at Bob's window of vitality, we may find a parallel to our highest security, but there are also rare ecosystems at the side. If we say the mainstream ecosystems might be located right here. And these rare ecosystems, of course, also have a certain value, and they can become very important, for example, for nutrition, or here we can see they can become very important for climate regulation if we need places for carbon storage and carbon sequestration. Then these edge systems can become very important for mankind. So this is also not the case to say the more the better. And then we still have resilience and adaptability. Resilience as the ability of a system to return to where it was before. So this is somehow a small scale dynamics around this developmental phases. And adaptability as the ability to move forward and complexify after a certain disturbance. If we maximize them, if we maximize resilience, we would have a very rigid and fixed system. And if we maximize adaptability, we would have a very uncontrolled and insecure dynamics. So also here, it may be the case that tentatively, mostly, most is not the best. Now, if we list all these different ecosystem features, which we have heard about before, and look at them a little bit critically, we can say that all maxima, as we have seen in the Bornholm Lakes example, somehow provoke minima of related components. And even the positive items turn to disadvantages when they are too strong. In the rare positions can become very important if we have a crisis situation. This means that for sustainability management, we have to look for multifactorial optimization, and high diversity is important. And before all, learning ability plays a very, very big role. So what we have to do within these systems is train the adaptive capacity of these systems, and be aware that sustainability is a compromise between all these different nice features. Yeah, so we come back to our initial question, and you know the answer already. The answer is it depends, but tentatively, in many cases, most is not the best. So thank you very much for listening.
Thank you very much, Felix. For me, it was interesting that you made quite an explicit link between some of the network properties and the ecosystem services that then could go on further to link back to Ika's talk again, how we use this in this social ecological system. And I could imagine that this theme will also be quite a fruitful one for the discussion session that we have now. At this point, I want to thank all the speakers that we had in this session. Thank you very much for, for really interesting talks on networks and related subjects. So we have about 30 minutes for discussion now before we break. And Valerie, because of all these messages in the chat, I don't see the questions anymore.
Yes, I just sent you the one that I posted in the beginning. I think it was initially addressed to Brian Fath, but I think also Bob Ulanowitz could be a good respondent to the question. I just sent it to you, Ursula.
I cannot see it.
Okay.
Oh, sorry. I can scroll down all the 800 and something messages.
Then I'm going to try my best to say it orally. So Bob, the question came up about the centripetality. If the system moves away from equilibrium, shouldn't that be centrifugality? That's what I can say from the chat, and that's the only question that was posted so far. But please, there is still time. Bob,
you're muted, Bob.
Okay, centripetality is something that people always have questions about. Okay, the idea is that you have a mutually beneficent cycle, okay? What happens if you have a change in one of those members? And if that change makes it more sensitive to the upstream member or less and better, or a better catalyst of the downstream member, it will receive more reward, okay? Well, conversely, if the change decrements either of those two, it will receive less. There's a basic asymmetry in all of that features the selection of changes that increase the autocatalysis. Now, a corollary of that has to do with the inputs, okay? If there is a change in one of the things that increases, helps it bring in more resources into the system, that will be rewarded. But that applies not just to that one, it applies to all of them, okay? So that the idea is over time, that autocatalysis causes centripetality, causes the intake of greater and greater resources. Now, from a thermodynamic perspective, you're absolutely right. There's more entropy produced, okay? But that's the universal balance. If the balance is on the system itself, it's definitely centripetal. Now, and I'll go even further. I'll go further out on a limb. Evolutionary theory is predicated around competition, essentially. But you can't have competition without mutual beneficence at the next level below. Mutual beneficence is primary. Competition is derivative and secondary. None other than Bertrand Russell, famous philosopher who talked about it as chemical imperialism, said that it is the major driving force behind evolution. And I concur with that.
Thank you very much, Bob. I think that there was also a related question to that right in the beginning, and it might have been directed to Brian, and that was what then has the centripetality to do with resilience specifically? How do these two concepts connect?
Yeah, so I think it also had something to do with circular economy and closing the loop as much as possible. So building off of what Bob had just mentioned, was that as that system is able to reinforce itself, it's able to, you know, take in more resources and get those benefits from that. And that's also, as has been called, the sucking up of resources as well too, though, right? So it's basically becomes a you know, a self-reinforcing flow. But then with resilience, and again, we've already seen several different definitions of resilience, and the last one being Felix's, which was quite nice as far as the band of width in which you're oscillating as you're going along an adaptive cycle. And so so thinking about the being able to maintain those positions that you're in there, not getting too far afield. So yeah, so I would say that the cycling and the circular economy is just allowing more of those resources to be used efficiently without having to either rely on external flows to come in and subsidize those, or just, you know, maintaining it longer in the system. Essentially, you're increasing the residence time of those flows, so as it's moving up the adaptive cycle. I mean, we have many different kind of definitions at play here, so I guess it depends on your definition of resilience. But definitely the addition of cycles is something, as we see, as a primary way that benefits, as Bernie was talking about, the synergism, the amount of, you know, as I was talking about, just through flow is increasing when you have more cycling. Indirect flows are increasing when you have more cycling. So yeah, the network development of cycling structures is evident in nature, and something that we think needs to be more prevalent in social economic systems. I'm not sure that completely answered, but.
Thank you, Brian. Would any of the other panelists like to contribute to that answer? Or have we answered the question for the attendee? We haven't heard back yet. But if you have a follow-on questions, then please post it. Yes, Bernie, please go ahead. You're muted. Bernie, you're muted.
You hear me now?
Yes. Perfect.
So if you take two entities that are transferring some substance between them, we represent, in a graph representation, we have node, and a link connecting them. But it's helpful for me, at least, to think about, to break that connection down into two parts. One, an outgoing part from the donor, and the other, a receiving part by the receiver. And they are connected in the middle by what we call an identity constraint of coupling. Okay, and that identity constraint is quite rigid in the sense that everything that meets that node, non-existent node in the middle, goes to the receiver that comes from the donor. So the centripetal process is experienced by the receiver. But the outgoing process, the donating process, is a centrifugal process. And what I'm trying to say is, aren't these two processes always reciprocally involved in any kind of network? It's hard to get one without the other. So look to Bob Ulanowitz for...
No, you're absolutely right, Bernie, that first of all, thermodynamically, on the whole, the system is dissipative. It has to be. That's the second law. And the two have to be balanced. The idea here is that mutualism, indirect mutualism, will cause the sequestering, as Brian talked about in cycling, cause the sequestering and the reuse of material. And also it brings in more from the outside. I mean, we see this in marine systems around coral reefs. I mean, you have this coral reef in a desert of an ocean, and when suddenly you come to the coral reef, and there's this enormous increase in elements and energy and everything, and it's all being centripetally drawn in and sequestered by the coral reef. I'd like to say something about your fields that you talked about, Bernie, because I think it's an important thing. You said that physics was objects and fields. John Hart, who works with thermodynamics and ecosystem, and I've discussed this as well. He feels that there's such a thing as an ecosystem field, which I think is what you're suggesting. And I think there's something to it, but it's going to be very different from a gravitational field or an electrical field in the sense that causality is distributed. Causality is distributed over the network. And that's something we're not used to, because even in physics, causality is always bilateral. This is not bilateral. It's multilateral. And it really is spatially distributed. And it's a form of a field, if you will. How to formalize that is another problem, and I haven't solved that. But I think it's something you want to do. We want to develop the notion of a field. Well, for example, I showed the little three mutual support and mutual beneficent autocatalytic calculation. There are examples of that in nature, the utricularia system, and I won't go into what that is, but the idea is that it tends to bring in and keep the material. And I've suddenly had a senior moment and forgot what I was going to say. Yeah. Okay, I'll just sign off for now and let somebody else take the discussion.
If I could follow up on, so what you're saying is that the fields are not just at a distance, but they're also multinodal.
Good point. Yeah. First of all, the utricularia system, the characteristic time of circulation of those effects is on the order of weeks, maybe months or days. Okay, very slow. On the other hand, it keeps on going. How does it do it? Because there are other informational transfers. Okay, there's chemical transfer, olfactory, visual, electrical, et cetera, et cetera. And these things are very fast. Most of them go at the speed of light or very quickly. And what happens, I think, is that the system, the individual members adapt to these informational transfers in such a way as to keep that cycle going. And it's called scaffolding. The biosemiotists call it scaffolding. And I think what you have is informational scaffolding of these loops of mutual beneficence. And that involves, of course, fields. Each of those means of information transfer depends on some sort of a field.
May I respond back?
Please do, Bernie.
Bob is an advocate of Popper and the notion of propensities. And isn't that a word that is suggestive of a likelihood of something going in a certain direction? And isn't that a field phenomenon? That's what fields are doing. Mm-hmm. They are directing energies and matters along pathways with different likelihoods. So that's one point. Bob, you want to respond?
I would agree wholeheartedly. And what I'm worried about is people taking too much of a didactic approach to fields and thinking that it's all like gravitation, like light, et cetera, et cetera. We have colleagues, if you remember Emilio and the lady's name, Larissa, who brought the concept of physical coherence domains into ecology. I think the dynamics of a coherence domain applies to ecology, but it's not in the literal sense of quantum theory, okay? It's not on a Planck scale. It's at a larger scale, a different thing. So we have to learn to translate these ideas like fields into something different from their appearance in physics. That's my point.
Let me give an analog of something that's commonplace in the environ approach that touches or could be made to seem to touch some quantum ideas. The idea that the electron is everywhere and nowhere in the universe, until you observe it, and then you get quantum collapse to the concrete, electron. So,
okay.
Wait, let me finish. In our area, we have environs, and the nodes in the environs are non-existent. They are everywhere and nowhere until you make an empirical observation on what those environs are represented, and then they all collapse and become part of that. So so I would then suggest that the differences between, there probably are more similarities and differences across the scales of organization if we choose to begin to develop that.
No, I would agree. And as a matter of fact, Diederik Ernst and Sandro Sosso at the Freie Universität Brüssel have an active research program going, trying to show how ideas from quantum physics apply to ecosystems. And you've just given us an example. And I think they are many. The thing that I'm warning against is don't take them too literally as quantum phenomena at the Planck level. Okay, I'm an engineer, and engineers— I
used the word analog in my description, and
yes,
for now they're analogous points. Okay,
and I agree wholeheartedly on that. I just warn against—
we might actually begin to discover some of the commonalities between the levels, and they're widely separated as levels of organization, obviously.
Yeah. Just as an engineer, I worry about mixing up dimensions and start talking about things that are valid only at the very microscopic level of subatomic phenomena, and suddenly transforming them to the macroscopic world without looking at the dimensions concerned. That's my only concern as an engineer.
We probably would agree, though, that causality in reality is uniformly expressed, whatever the levels of organization, and the constraints would be on the levels of organization themselves, and the inability of a propensity to be expressed at one level simply because there's a lot there that is different versus at another level, and so on. But pursuing the notion that laws are fundamental. Have any of you read Frank Wilczek's book called Fundamentals? It was last year, I think, came out, and it, for me, is a revelation. It talks, for example, I think the first chapter is there's plenty of time, and then it goes into time. And the second chapter is there's plenty of space, and it makes the point that there's more space inside of entities going downward toward minus infinity than there is outside. And especially to an observer, because an observer like ourselves, and this is why we have mechanistic and reductive sciences, because we're able to, with our own span of space and time, our own cognitive apparatus, we're simply able to go in further and more than we are able to go out. Things get very diffuse very quickly going out, but they get very dense going in. And we stop right now at string theory, which is what, 4 or 5 levels down. I mean, only, okay? But if we're going to minus infinity, but anyway, it's a fascinating book because it brings those kinds of perspectives up to the surface. And in fact, it was that book that began to trigger our attention to fields as being a part of what we've been doing all along, and just we've been using words like propensities and so forth and relations and because they fit our science, they fit our empiricism, they fit our concepts. But so the field theory presently is as much as we can begin to learn about it. Of course, it's all mathematics. When you start pursuing it, it's pretty high level mathematics. So it's for ecologists like ourselves, difficult areas, but conceptually, it's rich in possibilities.
Okay. I would just, in the beginning of my talk, I tried to emphasize that physics is all about objects and laws. Ecology is all about processes and heterogeneity. The laws of physics are all homogeneous. This is a limitation people don't think. We've got to learn to think about heterogeneous, massively heterogeneous systems, which organisms and ecosystems are. And Gene Odom, back in, was it 69 or something like that, had this thing in Science magazine, said that ecology has to lead us forward into the future. And this is what I'm suggesting. We're dealing with a very heterogeneous world of processes, okay? Very different from what physics treats. That's not to gainsay physics. Physics is wonderful and will keep on giving us beautiful insights into nature in the homogeneous realm. But we as ecologists have to develop a new direction to look at living systems, because physics has its limitations in accommodating life. Process thinking doesn't. Yeah, I should warn any students out there, don't repeat any of these things in tests. I've had people fail because at exams because they repeated what I said. They're not accepted ideas. They're all, you know, out there.
No, I've always been a little more vertically oriented than you, Bob, and so and that is to say one thing building on another.
Yeah. So
and that's a direction I find comfortable, even though it's very hard to get to the next level, perhaps. And
yeah, but you see, that's like what's his name, Daniel Dennett, I think, talked about evolution as cranes built upon cranes. Okay, I didn't like that. The only eureka experience I ever had, I was in my garden and I was thinking, no, that's terrible, that's terrible. And I looked over at and there was my muscadine grapevine. Okay, I planted it, it's set up a vine, it put out runners, it had grapes and so forth, fine. But then it also put down adventitious roots into the ground. And after a while, the main trunk rotted away and it was being supported by the adventitious roots. I think this is a better analog of evolution. It's not only just up, it's up and down. So yeah, you know, I am mixed up going up and down. I'll confess to that.
So thank you very much. It's fascinating listening to the conversation. We have a few more questions in the chat that I would like to read out. One is, how should self-feedback in compartments should be treated when assessing mutualism? For example, compartments retain energy, but interactions among them contribute to high overall dissipation. In brackets, systems redundancy is higher than efficiency.
I think a technical response would be to that, based on the mathematics, is that the self loops cancel each other, because the mutualism emerges from the utility analysis, which is the net flow between nodes. And so if a flow is receiving and sending the same flow to itself, then that just mathematically it cancels. And so you can keep it, you keep it in your flow matrix, but then again, it cancels and not shows up in the actual power series analysis of mutualism. Now, it would show up in the information assessment, though, I believe, that Bob described, so that it would contribute to the system's redundancy, but not, and it would be a more redundant system. But those are again different analyses. One is looking at the redundancy versus efficiency, and the other one is looking at the mutualistic interactions in the network. So somewhat of a technical answer, but that's how I would treat it.
Thanks, Brian. And we have one more question that asks, do you feel that communication and terminology and language between social and mathematical scientists needs to be more effective for the benefit of both? Is the meaning of communication not the effect it has on others? Both perspectives are tremendously important for meaningful outcomes from the interaction. Who would like to tackle this question?
And sorry, but it was also added from the person Rico De Faria. He asked and wondered if Ika Dannhofer would sympathize with the predicament.
I'm leaving the word to Bernie.
Just my own observation. We have a team, a group of mathematicians who work with us, and what they prefer to do is mathematics that is interesting. Mathematically interesting, and that doesn't always match problem areas that are of interest to us. For example, our group has been working now probably over a year on a simple interaction between two insects. And the mathematics has become, I can just say generally, has become really, really just overwhelming for people like me. But yet it's compelling to these people. And so they gravitate to it. And we can't get any of our other work done and any of our other ideas advanced for the moment because they prefer this. So that's one thing we have experience in working with our colleagues. And would that we could find a way to bring people to problems that we can define more readily from our experiences than they are able to. But once defined and cast in mathematical framework, it's incredible what can be done. So that is something that should be cultivated. And probably to do that, you have to put people together in dedicated places where they can rub elbows and meet in hallways and things like that.
But what I personally think is that you can actually learn a lot by learning from each other, and things like distributed causality being distributed is essentially what they work on also in the assemblage approach, where we also say a farmer is that the only one making decisions and implementing that on the farm, or is that actually, are the non-humans also being effective? So again, translating is careful, but I think that what Bob said is really important, is not take things literally, but the ideas behind it. I think that's really what we can learn from each other. And yes, in another field, it might be mathematically extremely precise. On a farm, that doesn't make sense because the complexity is so high that there is no way any of these models will actually be helpful to understand what is going on day for day on a normal family farm, with all the social thing, the economics, the ecology, the everything. But the idea and the propensity is another idea that's coming out there. Is strategy really the right thing? I mean, whatever that is called, but a propensity is another word that is also, I mean, I've read quite a lot about it in Chinese thought. Again, this thing is you incline propensities rather than have a decision and march on with full front. Again, the thing is, how do people conceptualize things in other disciplines? And does that help me rethink my own discipline?
Thank you very much for your answers. I see we have another question in the Q&A. We decided to treat it in the next session. I think, Bob, did you still want to say something?
No, I just said that Soren has his hand up, that's all.
Sorry, Soren. Please go ahead.
Thank you, Bob. I'm just using the tools available. So, well, I've been teaching in a topic called techno-anthropology for 5 years now, and I definitely agree that we need to harmonize much more than we do at the moment. I have students working with a new database called Gesamtes, which is fairly advanced LCA. It's building on Leontief's matrices, but they don't know who Leontief is, that he was an economist or anything. And it's exactly the same basis that is used for both Bernie Patton's and Jovanovich's approaches. And we are simply not multidisciplinary enough, or we're not good enough in teaching that kind of education at the moment. Well, in addition to that, you're facing all the things that Ika mentioned with the farmers, et cetera, so the more distributed solutions. And I've tried to have students working with farmers and networks analysis and so on. And it's almost impossible because the farmers are so individual that, well, at maximum, you can group them into reaction patterns, but that's it. So, but I'll come back to that on the openness, I guess. So,
yeah. With regard to Ika's point, my first book had a lot of equations in it. Never sold anything. So the next two books, there was almost no equations. The idea is to take these the results of mathematics, which is wonderful, and put them into simple terms some sort of an aphorism and so forth that any educated layperson can understand. It's a very difficult task, but it's necessary.
And I think that's why you might have noticed that I use a lot of comics. I think that it's one way to get messages across. And if we want to contribute to the transformation of our society, we need to start to learn to communicate with people who are not expert in our own field. And yes, I agree, it's extremely difficult, but I do think it is a responsibility that we have, because if not, we just stay in the ivory tower and we do wonderful development, conceptual development, proofs. And I really believe strongly that they have value, but we shouldn't just talk to one another. We need to talk to other disciplines and to everybody. And that is also a responsibility that we have as honestly, as people paid by the taxpayers. You know, what am I giving back to them directly?
Thank you very much. I think Valerie is putting us onto the next point, and that is break. I want to thank all the speakers in this session, all the panelists, and all the attendees for your questions, and we'll see you back in 10 minutes. Thank you.
Next session for session 2. And I'm happy to hand over in this context to Fabiana Morandi, who will chair the next discussion round and present the speakers. But first, I want to present you, Fabiana. Fabiana Morandi is a mathematician with a PhD in chemical science with many years of international experience on sustainability assessment. And she's author of several scientific papers, both on theoretical aspects and on real case studies on sustainability assessment for territorial systems, such as urban systems, for logistics, and for different kind of production processes. So Fabiana, happy to hand over to you for introducing our next speaker. Thank you.
Thank you for introducing me, and I'm happy to introduce my 4 panelists. And I remind them that you have 15 minutes each to present your talk. And I'm happy to introduce Soren Nielsen. He has more than 30 years of teaching experience in system analysis and modeling, physical chemistry, environmental system management, toxicology and pharmacokinetic models. And he held about 60 courses in several countries around the world. And is also author of many scientific papers and several books. So please, the floor is yours. And I remind the audience to put all the questions in the Q&A box. Thank you.
I'll see if I can manage to make a screen share.
Yes, perfect.
Yes, okay. Sorry for this. Well, I would just want to say that I'm actually honored to be attending this session because in 1984, I joined a group here in Copenhagen that actually tried to convince politicians in Denmark that we should join IASA. Unfortunately, we never succeeded. So it has been a fight for 30 years, as Fabiana referred. I was rephrasing this a little. I will talk about this openness, which is giving problems when you do management. And it places us really somewhere between the constructive side and destructive side of ecosystems and society, for that matter. And also what we might face now is actually that we are going to do a lot of reconstruction after this COVID situation. So all of it with openness actually came out of questions from our group that what is it when we do management, what is good and what is bad management, and how may these opennesses, I always will talk about two now, how will they, an improvement of our understanding contribute to improvement also of the management. We can talk about different types. This is more or less trivial, but humans tend to interfere a lot with the society and nature, and particularly agriculture, which has been my interest for the last 4 or 5 years now. since I spent 1.5 years on the island of Samsø, which is considered partly sustainable. So all in all, what do we need to consider when we are doing this? And quite trivially, it has been addressed by several of the other authors. We are facing this enormous complexity of the nature. And we have to, and we know that as ecologists, that we need to get used to the variability and the adaptive properties of the ecosystems. So previously we have also talked about the complex adaptive systems. So we have some organizational issues, which has also been addressed up to now, ontology and phenomenology aspects. What I would like to stress here is, first of all, that we have this hierarchical organization, which is important when we discuss the entropy issues and also information issues, which can come out quite different, as Felix also said, depending on the situation. So, but we tend to use them in a, I would say, pretty disorganized manner, and this is what we're going to be better at if we are going to talk to people. But all in all, we need a better understanding of the ecosystem. In fact, I'm talking, as I said, about two types of openness. When I first started to work with this, I saw them as quite opposite, as quite, I would say, almost contradictory to each other. But right now, I'm of the attitude that none of them can actually live without the other. Both of them have a destructive side and a constructive side to them. The thermodynamic openness is probably the most well-known. It's coming from the second law of thermodynamics that we will have a look at later on, just to summarize what my opinion is around this. But destruction is dictated by the second law. Everything, there's no free lunch, as somebody stated it, and everything will strive at an equilibrium to the most probable distribution of particles. On the other hand, it has also ecosystems and biological organisms has openness to matter, which actually make it possible for them to grow and organize. Ontic openness, which is quite new, I'll try to explain it in a few seconds, is a less known feature, and all biological systems are of that kind. Also societies are ontic open. The destructive side is that this really high number of combinatorial possibilities that the system can read will inevitably lead to a decay. But it also constructive because that is where all new solutions to problems will emerge. Just to recapitulate some of the history, Boltzmann and Gibbs already did some consideration of the importance of thermodynamics to biology, but they had no ecosystems that appeared much later. Lotka also did some speculation on the free energy importance to organisms and minor populations, in particular of in decaying systems. Schrödinger made this unfortunate statement of living systems feeding on neg entropy, which actually gives the picture that something like negative entropy can exist. And I think that caused a lot of, or is the crux of much of the confusion in the area. Prigozhin and co-workers started out with postulating that biological or far from equilibrium systems, I should say, would develop towards a minimum entropy production. James and Swenson went exactly the other way around and stated that every system would develop into a maximum entropy production. Jürgensen and Kay and Snyder made both a fourth law of this and formulated it in terms of exergy. In principle, what we talked about earlier is the question now about the storage or the dissipative processes of the system. And we will have many more. I've given a reference for a historical review that we just made, some of us in this context. As Bob Jolanovic also mentioned, this has a tendency to develop into a very, very unfortunate set of metaphors and leading to a directly mechanist understanding of what organisms and ecosystems are about in energetic context. And together with reductionism, which was, I agree, is pretty successful in some contexts, but it also has had the consequence, unfortunately, that we have refused almost to talk about the wholes, and that is the system capacities or properties, features, including something like emergent properties and the teleological development that is possibly going on in ecosystems. We have some really theoretical problems that we need to address. That is that something like entropy is simply not very well defined far from equilibrium conditions. So we need to answer this simple question, what is entropy actually in this sense? And well, should it actually develop towards a minimum or maximum? You'll see, I tried to summarize my opinion on this one. Maybe it should be rather a corollary than a conundrum, but at least taking into from a quantitative point of view, if you have accounting for CHNOPS, as Moravec stated, you have accounted for 99% of that is going on in the systems. And we also have to consider that from cell and upwards in the biological hierarchy, everything, or downwards actually, it's physically bounded, but we have constructed as humans the boundaries of the ecosystems upwards in the system. That gives some limitation to our understanding of the openness. So what I would state is that the thermodynamical openness, the continuous flow of the energy and matter, makes it possible for the respective focal systems to organize the elements and getting to develop steadily more advanced stages, what we know as evolution or development. The primary ecosystem input is actually coming from high quality entropy from the solar radiation. And in my context, nothing would happen on Earth if we didn't have this photoautotrophic components, which is the basic of everything in society. The major component bringing into our living conditions is agriculture. There's also the material gradients, which make complexity diversity higher. This is known now from mountain regions that is having a high, unexpectedly high diversity. So we talked about system closure, circular economy. They are highly efficient ecosystems by this bounding and keeping by recycling of material matter, detritus and proteus, keeping the materials inside the systems. So what they do is tend to accumulate as much as matter and energy as possible. That is maximizing exit storage. But larger structure, on the other hand, also have a higher dissipation. But if you refer to organism level, at least Soten and Sotener would claim that it's leading to a higher efficiency. So eventually it's leading to a relatively lower dissipation density. I've just tried to illustrate it. You on the left-hand side see a development of an ecosystem through the time. And now you see on the right-hand side, you will see how I conceive it, that the system will develop around some lines. I'll come back to a similar picture later in this talk. And the system can stay in operating points and bifurcate and so on. And from all of these will be thermodynamically efficient state, and you will see an increasing efficiency of the systems. But what about the other openness? It's coming from the quantum physicists Walter Elsasser, who characterized biological systems as being heterogeneous. That was, I think, Jolanovic mentioned that. So, as opposed to the homogeneous system that he was used to work with. Heterogeneous system has the feature that they easily, when you calculate the combinatorial possibilities on them, they will lead to numerical explosions, leading to what Elsasser called immense numbers. They're really incredibly high. And I think Johannes always mentioned this possible way of calculating. Elsasser sets a realistic limit. It's 10 to the 100, a number called Google, over which all numbers are considered immense. So if you consider something like a COVID virus, a simple cell. Well, let's take the COVID RNA string, has a length that is actually having a consequence that it has 10 to the 18,000 possibilities combinatorial. This is really enormous complexity of the situation. And this means that everything can happen, and this is what we're seeing at the moment. The disadvantages for many of this is, as referring to one of the first slides, is that we always have to base this on some ontological elements, and it's dependent on what level of hierarchy that we're doing it on. What we can deduce from a property like ontic openness is that something will happen in the system. We have the variability element of neo-Darwinism guaranteed. Remember that this is an assumption behind Darwinism, but it's really, the causality is never really addressed. It's just there. That's something is actually unpredictable. It will have no direction. So there's no selectional mechanism. It's ontic openness. It will take any random way that it could be. It may be positive, negative. In Harry Rubin, one of the, I would say, followers of Elsasser's and implementers of Elsasser's principles in his science, he sees already from day zero that systems are disintegrating and disorganizing, and well, he equates that with disease or aging. In a positive way, we could actually see that we can improve the functionality, like in autocatalysis. So we go towards an increased efficiency, and this is what we see now in the COVID situation, that some of the coronaviruses are competing with each other, and the more efficient of the new varieties will actually start to be more successful and win the game. This is in particular important because the size of the genome for a coronavirus guarantees that you would have 2 to 3 mistakes equalized with mutations per replica. Remember, we have a lot of people infected and a lot of viruses going on. So there will be a lot of replications going on, a lot of mistakes, and in particular, coronavirus have no proofreading system. So it's just there. Revising our picture of this kind of system, every ontic open system will behave within a limited tube. The tube is not a regular tube, it's bulky all over, but the systems that we normally consider as common are behaving somehow within these limitations that are the constraints of the system. All are possible viable solutions, we will not be able to distinguish them. The other point is now that when we see such line evolving, they will leave out a lot of void space. And I fear actually this is what we will see right now, is that the void space will, for the coronavirus, start to be exploited. Normally, it's not accessible. It has been so heavily constrained that will not be a possible solution for us. Trying to illustrate the directionality in it, at the point of every line of these tubes, you will see a possibility that you will have this positive change of a line in the system due to ontic openness variation, or you will see the great regression winning of the system. I tried to explain that in a genetic context together with Klaus Emmeke, which is a former study comrade of mine, and he was actually the one introducing me to Elsasser in 1995 or 6, where Sabine Bauchmann, a German researcher, came and talked about Elsasser and ontic openness for us here in Copenhagen. So much of this and the ontic openness is also operating on various levels of hierarchy. So it penetrates everything. So we have no guarantee it can penetrate different places in our handling of COVID situation. You have ontic openness within the system, within the COVID virus, but you also have it in the reaction pattern from the people, ordinary people in the street. You have it from the politicians. So that makes the whole thing much more difficult to handle. And the same thing with environmental management systems. So what I would talk about to management now is that I have another conundrum here, is that at a genetic level, when we're talking about biodiversity, we need to ensure that the variability of the genome sequences available are maintained. And this is simply managing as if we have an ecosystem that should keep its ontic openness. What we see is that actually you can calculate that if you go down in number of threatened populations, they are reaching a size where they are simply not ontic open any longer. So we are experts in disturbing these, reducing the life space viability of the organisms. One example is that the neonicotinoid impact on the insects that are heavily impacting the bees that should actually serve to fertilize our vegetation and thereby damaging our ecosystem services and affecting our societal resilience. So in the same manner, whole ecosystems are likely to be impacted now, and we are going to have a movement of climatic zones likely towards the north. So, both type of openness deals with some sort of information storage. This is where I'm trying to research at the moment. Whatever does information in this context mean, and how can it assist us in addressing the problem? So that is both the Jovanovic approach with the network information and also the information on the ontic particles themselves alone.
I'm sorry, but time is up. So
okay.
I don't know if you have only 1 minute, you can finish. Or
this is the final slide.
Okay.
So I would claim that in order to maintain the ecosystems at a sufficient functional level, we need to consider both types of openness. They need to have a functionality, and they also need to have some variability. So I think that was actually where the previous session more or less ended. But at present, our societal activities are disturbing actually both of the activities. So I just want to be sure that the second last point is actually what I think is dangerous is that this is now, from a politician point of view and management point of view, being just a demanding of functionality of the nature, and they tend to not give a damn about the biodiversity of the systems. We see that here in Copenhagen, the moment 1 kilometer where I'm at, 7,000 years old ecosystem, 12 to 20 red listed species in dangers, and yet they insist on building or constructing on the area because we need to have Copenhagen to grow. So that's it. So all of this is just references, the rest of it, and ways to have a view of it.
Okay,
so,
thank you very much for a very interesting presentation. And now I introduce Simone Bastianoni, next speaker. He is a full professor of environmental chemistry, chair of the PhD School in Environmental, Geological and Polar Sciences, and provost for sustainability at the University of Siena, Italy. He has more than 30 years experience in investigating sustainability indicators, and he has published more than 200 papers, and he is also co-author of some monographs. So the floor is yours, and keep 15 minutes, please.
Okay, thanks, Fabiana. And it's exactly 30 years, actually. No, don't make me older than I am, please. Actually, 29. So but anyway, yes.
But I want to remember that he was my professor, and I see him very old.
Yeah, that's why. Okay. Yes, I will, for my talk, I will rely very much on what all the previous speakers have said. It seems like we have written a book together, actually. So, how does it work? I don't know. Okay. So I will start with sustainability, just the two things that have been around for decades now, the sentence from the Brundtland Commission and the representation with the three spheres partially overlapping. I think that these, especially the representation of sustainability with these three spheres have been a problem for the whole sustainability concept, because it shows three dimensions that are, as I said, only partially overlapping. So it seems that there is an economy that does not rely on the environment or on the society. And this makes, I mean, people think that these three levels are more or less, let's say, the same, independent. And since up to now, since the economy was the most urgent thing, with the one for sure with the, let's say, turnover time that is shorter. So we should take care first of the economy and then of the rest. This has been a failure for the whole sustainability concept, I guess. And we rather use this picture here in which we have the environment at the basis of a society and the economy as the tip of the iceberg, let's say, of the society that is the useful aspect of the society. But after we draw this picture, it came to our mind that there was another way of looking at it. I mean, flipping it 90 degrees. Because this is a much more friendly way of seeing things, and quite usual for many to see things from left to right, and because you can see these as a cause-effect sequence. I mean, society relies on environment. We eat environment. We eat in a very broad sense. We use environment for anything that we do in our society. And economy, in fact, is the useful output of the society that, I mean, should be useful at least. And so the society is at the center of our, for sure, at the center of our analysis, because sustainability is just for the human society. I mean, environment by itself is sustainable for sure, and maybe it would stay much better if we were not here as a human species, but we are, and so it's our duty to deal with this situation in the best way we can. So this is, let's say, the summary of the thing, in which we have an input that is the environment, that is input to the state of the society that we want to organize, and the output is the economy, as I said. So is an input state output situation. And obviously there are feedbacks from the economy to the society, to the economy to the environment, and from the society to the environment. And they can be, generally speaking, not technically speaking, positive or negative. I mean, waste production from the economy or the society are for sure examples of negative effects on the environment, while the payback for people, I mean, for workers, for example, is a good feedback from the economy to the society. And just to go back to the COVID-19 situation and this representation, we can say something about COVID-19 and this representation, because this COVID-19 crisis has shown exactly how things work, I mean, in this sense, because first of all, we had an environmental crisis in the input phase in which humans and animals interact in some ways, and all of a sudden a virus jumps from an animal to a human, and then everything starts. Then we are having a crisis in the society because I mean we need to have lockdowns, etc., or reduced activities anyway, because otherwise we get too much sick. And obviously, the third crisis is the economic one that comes because of the ecological crisis or environmental crisis and of the societal crisis. So in this sense, every time I hear that we have to open because of the economy, etc., well, I guess that those that want to reason just here at the end of the chain forget that the cause-effect situation and the feedbacks. So in this case, those that want to open more for the economic benefit, eventually that will make the economic something bad to the economy. We have shown this situation also for analyzing the economies around the world, and we found out a curious thing that basically the big the big connection is between the consumption of goods. So in this sense, the amount of environment that we use as society and the economy. The society itself, the organization of society, is like jumped by this cause-effect thing that connects the use of resources and economic growth, let's say. But this is not what I want to stop with, but I want to go back to the environmental part. Because if we zoom on the environmental part, we find, as the previous speaker showed, the same situation as we have seen before, in a sense that is always, in natural systems, input and a state and some outputs. In this sense, if we want to see the thing from our viewpoint, or our viewpoint in the sense of human race, the input is coming from the sun, from the rain, the wind, etc. The state is the state of the whole biosphere, or of one of the ecosystems that you want to analyze. And in this sense, the useful output are the ecosystem services of which Felix Miller talked before. So the inputs arrive in the ecosystem, the system organizes itself in a structure, and at the end, we use the output of these ecosystems as ecosystem services. Going to the orienters or indicators, or how, I mean, we want to call them, energy is something that works in the input phase of the system, while entropy, ecoexergy, network analysis work focusing on the state of the ecosystems that you want to analyze, and ascendancy instead works, let's say, coupling the state of the system and the input going to the system. This is just to clarify where we stand. And if we couple this representation, the environmental part of the representation and the human part that I showed at the beginning, we have these ecological plus economic systems put together, and we can make it more understandable in this way, because ecosystem services can reach our system as ecosystem services per se, not being transformed further, like purification of water or air, and something that is not, or pollination, for example, something that is not really transformed by human beings, or as the resources that are transformed within the society and the economy to produce useful stuff for the society itself. And in this sense, you see this representation is a bit more complex, but has all the things that we had in the input state output representation of the sustainability, let's say, and of the environmental part and the ecological part zoomed in the green picture. At this point, we can see for each of the sustainability assessment approaches or indicators, we can show in this representation where data are collected and what is the area of interest of the approach, so that you can understand better what these indicators or approaches are are actually focused on, or what they should be, let's say, apt to describe. Okay, so just to start, I show you GDP. GDP, you know what it is. I mean, it's not a sustainability indicator, but just to show you, GDP works here. I mean, it takes the data just from the economic system, the production of the economic system, and the interest is this. Okay, this with respect to this. You have heard, I guess, of ecological footprint. It turns everything that we use into land requirement to produce something, so that we can understand if there is enough land to support in a sustainable way our consumption. It takes its data when the resources enter the society, and this is let's say, the area of pertinence of ecological footprint, in the sense that starts from where the resources are taken and goes back until the economy, and then it feeds back just with one part, because it takes into consideration the pollution due to CO2 and other greenhouse gases effects, greenhouse gases. In this sense, it takes also into account these feedbacks. If I look at LCA and other of the approaches that are very commonly used, and it takes, and it basically wants to assess how much impact, impact that we, possible impacts that we can have in a certain production system, for example. And in this sense, the point of where we collect the data is where resources enter the production system and the socio-economic system. And the LCA goes from let's say, the society, economy, and the feedbacks to the environment, because it measures how much impact we produce on the environment.
I'm sorry, but time is up. So
okay,
please.
I go very fast. With energy, we have 3 points where we collect data from renewable resources, from the input, then the state for the non-renewable resources, and the same as the previous one. So, and energy doesn't consider the feedbacks, but just the direct flows. And ecoexergy basically goes on the state of the ecosystem, and it goes here. And then exergy per se, or extended exergy, can show something on the societal part where the technosphere works. So this is the summary, but I will not show you. So just a few seconds to scroll. This shows where we can we work when we do sustainability studies. The conclusions. Ecological principles highlight the cause-effect relationships between the sustainability components, and the input state output representation helps clarify the role of different approaches and showing this way the overlapping and complementarities of these approaches. This overview obviously is not complete, also because I knew that there were 15 minutes, and consider that up to now policy is based only on the last part of the graph, that covered by GDP basically. And I maintain that Simpson perspective should be adopted also at the policy level, in the sense that all what I've shown you should be considered as a whole, and policy should be focused on the whole thing and not just on pieces per se. Thank you very much for your attention.
Thank you very much for the very nice presentation. And now I'm going to introduce Carlos Marquez, hoping the pronounce is fine. He is a marine and estuarine ecologist, and he is a full professor at the Coimbra University in Portugal. He is director of the Marine and Environmental Sciences Center, and he has worked on biological and ecological processes in marine and estuarine ecosystem, system ecology, and ecological modeling. He has coordinated several research projects and published more than 300 scientific papers, as well as several books. So the floor is yours. 15 minutes, please. Thank you.
You're muted, Joao.
Yes, you are muted. No.
Unmute. Okay.
Okay.
Okay. Thank you for the nice presentation about myself. I wouldn't say better. Okay. As marine biologist, as Fabiana said, coastal ecosystems, namely estuaries, has always been at the center of my research interests. And having started as a conventional ecologist, from the 90s, I started interacting with people like Brian, Soren, Sven, Simone, Felix, and so on, and so on, and so on. And I brought to my field of research many of the concepts, topics, and knowledge that you heard before in the previous presentations. Okay, and I will try to contribute to the final discussion in this workshop, this webinar. When you talk about coastal systems, you talk about something that is complex, because coastal systems depend on coastal processes. Coastal processes are defining the coastal form, basically. They include, of course, erosion, weathering, deposition. They have a particular spatial and temporal dynamics. And what we have hacking are waves, wind, tides, currents, sediments, of course, that are controlled by these elements, but also that control the coastal form. All this is supposed to reach a certain dynamic equilibrium. But climate is a new aspect that we have been exploring when we look upon coastal ecosystems, because it influences not only the external marine influences, but also the external terrestrial influences that act on the coastal ecosystem. We are talking about bigger waves in the winter. We have been observing that. The amplitude of the waves is increasing, stronger storms. Of course, we talk about sea level rise, and all this is connected with temperature rise, related with CO2 concentrations. This implies that runoff is also changing, sometimes increasing, sometimes decreasing. All this affects the coastal system. That includes the natural subsystem, of course, and the societal subsystem. Why do I look upon coastal systems with such an interest? Because most of the human population lives along the coastal systems, and the human activities are so complex in coastal systems that creates an incredibly interesting problem to be managed. And actually, this is a very tricky puzzle to manage. Usually we use this deep sea approach. Of course, we have the drivers that are proceeding from our needs as a society. We have the activities that are supposed to fulfill our needs, but that creates pressures. Pressures can change the state of the system. This will impact on the welfare, so we need to respond in some way. So we have measures that might be legal, it might be economical, it might be from the engineering point of view. Of course, the measures are going to influence the drivers, changing it, but they can act directly on the activities or on the pressures. So this is a complex system where ecological sustainability must always be seen within an ecosystem integrated framework and ecosystem integrity framework. And to reach this is really a crucial challenge in terms of ecology and the science of ecology. This is a more detailed view of the previous slide, and I'm not going to enter in detail on this. Adaptive management cycles, you all know about this. But what I want to emphasize in this slide here is that climate change is basically acting on the pressures. And that's where we need to focus when we want to include climate change in the equation. Well, we have many options. And the options, as we have been seeing in the previous presentations, are very much driven by political choices and societal choices. Many people would like to go business as usual. It's not possible. It will not be possible. But also, people that want to go deep green are out of reality. We will never be able to go deep green because the human population is already too big. We are already used to a certain type of approaches. So we are already trapped in our situation. We cannot return to deep green. And one of the approaches that is possible and has been undertaken, namely in Europe, but also in US and Australia and lately in China, but also starting in South Africa, is the policy target approach, in which we establish policy objectives that normally have connection with the environment, establishing a kind of proxies in the environment. So situations that establish thresholds that we are supposed not to overcome. And those thresholds anchor the system in such a way that if we respect the thresholds we establish, we are forced to adjust all the rest. When we look to this, we understand immediately that this approach and sustainability as a whole, sustainability science, is very complex and uncertain. You have been seeing this in all the previous presentations, from the more detailed approaches up to the more holistic ones like Felix or Simone. You have been seeing that. But there are three drivers that we always have acting on us. First, we look for our human well-being. and to maintain our human health, our safety, our security. But we know that this is a short-term endeavor if we don't respect the endeavor of keeping ecological sustainability and environmental well-being. Because if the environment collapses, of course, our search for human well-being will be deeply affected and will probably collapse as well. But if we look to these two drivers, we cannot forget the third one. That is, when we look to our well-being, we create pressure. And one of the drivers that must control what we do and our choices is what is the tolerance that can be said as resilience or resistance or the concepts that were already visited here of environment and nature as a whole regarding the pressures we create when we demand and search for our wealth creation. So when we look upon this, we see societal basic needs need a sustainable management. Okay, if we try to put these three drivers I just referred in a figure, it looks like this. Okay, a trigon, a sustainability trigon. If we take the policy target environmental objectives, we can put it at the base of the trigon. Of course, we can use a lot of approaches to consider this kind of environmental policy targets. We can use ecosystem health, we can use ecological sustainability, probably in the weak sustainability definition. We can use a lot of ecological indicators. I've been working on that for many, many years. We can consider ecological services and goods. We can consider resilience. We can preserve natural capital. Okay. Anyway, when we establish a threshold of what is acceptable and what is not acceptable, we are going to anchor the system here and somewhere in the threshold value that we establish. In the left side of the trigon, we can look to the ecological, sustainable, economic alternatives we can have. As Simone said, in many cases, political decisions just take into account GDP, for instance. They concentrate on the economical sector. But at the local level or at a more local level, we can look to stakeholder benefits. We can also look to economic services and goods, which can be distinguished from ecological services and goods. And we can actually also use well-being indices that are more sophisticated in terms of more subjective as well, because they are not just focusing on the product or on the production, but also on other more subjective aspects. But if we look upon our search for well-being, we are going to create pressures. And as much as we look to our well-being, the stronger will be the pressures we create. And if we anchor the system in order to respect a given threshold regarding the indicators we use, then we need to find environmental solutions. Yes, okay. Environmental solutions that keep the system anchored where we decided that we wanted to keep it, and so they can deal with the pressures we create, but the solutions will be more and more complex. And if they become more and more complex, they become more and more costly. Other speakers, previous speakers, also approached this question. Revisiting this, I will say that, and Felix also, and Bob Olanovics also referred this, we cannot maximize each of these aspects. If we try to maximize, anchor the system in a very, very demanding threshold, basically our activities will not be possible. But we need to have it. Otherwise, we cannot sustain our well-being. So we need to anchor the system in a realistic point in terms of indicators that we want to respect. We need to look upon our well-being from a realistic point, and keep the pressures at a realistic point, meaning that we need to optimize the system. We cannot maximize. As Felix said, the most is not the best. And I totally agree with that. We need to optimize, not maximize. In this right side figure, I show where applying this approach to the Mondego estuary, this is in the western coast of Portugal, and I've been studying it for many, many years, and applying the Water Framework Directive, the European Water Framework Directive, and the indicators, multi-metric indicators that we adopted to the directive, and through the application of a number of mitigation measures and also recovery measures, which I cannot go in detail, only 15 minutes. We brought the system in the last 20 years from the position A to within the optimization area of the trigon. Why can't we maximize? This was also shown before, has been shown. If we maximize and we consider the relation between the cost of the solutions we need to implement and the complexity of those solutions that are necessary to keep the system anchored in the threshold we established, the costs will increase not linearly but exponentially, meaning that when we relate the benefits with the complexity of the solutions we are forced to adopt, the benefits at a given point will decrease, unless we are not internalizing the costs in our product. Because in many cases, and that's also a political decision, people act as they want because someone is paying the polluting, someone is paying, for instance, subsidizing production. Of course, the costs of keeping the environment in good shape will not be internalized in the final product. But if they are, at a given point, we need to choose another activity that is compatible with that kind of sustainable use of coastal ecosystems. This is a transdisciplinary problem and it requires innovative ways of thinking. All these disciplines, I try to summarize a few here in this slide. All these disciplines must be taken into account, but more than other thing, we need to build bridges between all these disciplines in order to deal and manage in a sustainable way coastal ecosystems, but this is applicable to ecosystems as a whole if we want to apply the ecosystem approach. I hope to have contributed to the final discussion that we are going to have in this webinar. So thank you for your attention up to now.
Thank you very much for the presentation, very nice, and to keep the time of 15 minutes. So now I'm going to introduce next speaker, Harald Katzmeier, hoping the pronounce is also fine here. He is founder and director of FAS Research, and thanks to his international experience and the knowledge acquired in more than 2,000 international projects, he actually is one of the world's leading experts in the field of applied social network analysis. His background is in sociology and philosophy with a doctorate in philosophy, and he has taught at various universities in Vienna. So now the floor is yours. I remind to write the question in the Q&A box. Thank you, please.
So my first question is to you, are you still alive? So still some exergy, MRG or whatever in your body? Good, good, good. So this is now the last talk. Of course, I've got too many slides. So let's see how far it gets. So I want to talk about our innovation ecologies and how to design innovation ecologies in practice. So I talk about an actual project we're leading here at FS Research, and about the theoretical background and foundation. I want to show you how valuable our ecosystem thinking and the models that we've talked about today and we've heard about today are when we apply them in practice, even like in a social realm. And first up, I would like to start with, when we talk about innovation, what do I mean by innovation, right? So where does novelty come from? And there's our, the first school of innovation number one is there's a creator, a God, and he just like, because he's a genius and there's all the power, creates the world, or in this case, Adam. This is like the 1.0 version. Of course, he's not just like creating, but he also is destroying the world. So he's a destroyer. And the fatalist version of that would be like the novelty comes into the world through blind randomness. So it's quite a simple, straightforward model of innovation. Much more complex is the Hellenistic model. As you know, the gods in Greece, they had to procreate. So they're size and hair. They had to have, and I say it how it is, have less sex. So have to recombine genes in order to bring forth something new. So procreation always means 1 + 1 is 3. And each time you hear out there, we have to build places where ideas can recombine. That's the story. It's the Hellenistic story of procreation. So ideas gotta have sex with each other so that 1 + 1 = 3. There's another version, and it's the Chinese model, and it's like the yin-yang thing. It's a gradient inducing opposites. You have a diversity gradient, like the flowing water and the solid mountain. And because of the polarities, there's like a gradient that creates, so to speak, the atmosphere where life can emerge, can regenerate, but also the new can grow. We, of course, here in this community are linked with this model. And its novelty is the product of autocatalytic emergence. But when you think about it, it's actually a recombination of the Greek and the Chinese model, because you have the recombination model built in there, plus the diversity gradient that is actually part of the whole theory of the adjacent possible, and the theory, the model that networks constantly get sucked into the opportunity, the new niches that itself has created. So you see, like a novelty is like the product of a process where a network, through the interactions and through the recombinations, creates a space for the next step where the new niche can actually emerge. And here's just another representation of the emergence of ecological and economic niches. And the question that we try to address here is it possible to design something like that, to have a network that has these emergent properties to bring forth novelty, and what would be the shape of that network? So how would it work? And here is like a map of Linz, of Austria, the Tobacco-Fabrik. It's the old Tobacco-Fabrik. It was a brownfield, and it was a huge area. And the question is, how can we create there an innovation ecology with startups, et cetera? So how can we create their autocatalytic culture, an autocatalytic network that novelty finds its place there? Well, is there a blueprint? Well, let me go one step back again. So I've talked about the novelty space. So each time, every network has what we call a latent niche space grid. What do I mean by that? You have a network, and a network always has like an adjacent niche space. The niche space is represented through those dots, those white dots, okay? So, and the important thing here is this, this latent space has different shapes. So you can have the same network, or you have similar networks with completely different, let them call niche spaces. Why is that? And that's something to do, there's the tip with culture. Look here, this is what I call the closer syndrome grid, named after Jane Jacobs. I deeply admire, and it's linked to her book, The Systems of Survival. Think about a tribal culture, a bureaucracy, or a political party, or an army. They would have like a network like that. There is no adjacency space. Why? Because it's taboo. It's forbidden to deal with the other. It's just like there's a taboo function, a cultural function that you gotta shun trade, that you've gotta shun trade, excuse me, with foreigner. You're not allowed. So the soldier is not allowed to deal with the enemy. Only the generals might be allowed to speak with each other. So their opportunity space is very, very poor. Whereas in the commercial context, you have a lot of opportunity to walk into the white space. So structural holes in networks can have completely different meaning depending on, so if you're in a power elite network, life is full of potential next steps, full of opportunity, so that the grid, the latent grid of potential niches and roles is much, much richer. So but things are much more complicated than that, because we know that networks, complex systems, they cycle through different stages. So they're not static. There's not the network. There's not the grid. It's much more dynamic. And we know this from Buzz Halling and H.T. Adams and Ulanowitz model it's all like linked with, we have dynamics. And here you see like an example how the opportunity space changes through the cycle. So here at the peak of the growth cycle, there's a rich space of opportunity that you can, where evolution or technology can do its next steps. So here, when action is constrained, it gets poorer and poorer. And after breakdown, there's no place to go. You're simply, it's empty. Whereas at this stage of the cycle, anything seems to be possible. So between anything's you could walk everywhere to actually nowhere. Everything, the world seems to be closed. There's no next step. You're trapped in the status quo. There's different stages. So the art is how to design a network where you can go through those cycles, because actually in the real world, the cycles are erratic. There is not a beautiful cycle in the social world. It's not like our summer, winter, spring, and each have a kind of like a similar time span. In real world, there's not just one direction. I mean, sometimes you move in the real life from spring directly to winter, or from fall directly to spring. So you have much more, in the social world, we don't have this clear cycle. So there's irregularities, and of course, it's multi-scale. So it gets so complicated and complicated. So what is our approach to that? And this was the inspiration by reading Joseph Campbell's Hero's Journey, and also starting to dig deeper into our Carl Gustav Jung's theory of archetypes. So every step in the cycle, every stage creates its niches and its roles. And those roles are opening up the opportunity for other roles. So every every role, like in the emergent niche model that I've showed before, is opening up the possibility for the other role to exist, so to speak. And here you see like archetypes. So it's a very simplified role model of our world, because you see you have the seeker, you have the lover, the creator, the fighter, the ruler, the fool, the jester, the destroyer, the orphan child, the healer, the prophet, the sage. You might sound, this like sounds really strange. I mean, this is not like modern sociology. It is not, but the types, the roles that you see here make a lot of sense. Give me an example. First, this is just like, I will come back to this later, because those roles, as I said, are competing and completing each other in the cycle at different stages. And you can see like that there is like an interaction, how those different roles, mythological roles, open up the door for the existing, or preparing, so to speak, the conditions for those others to create or even to exist. So that's an example, the seeker. Think about the explorer. How can you have an innovation ecology without explorers, without the autonomies? That's, by the way, Jane Jacobs, a beautiful picture. The gold diggers, the loners, the mavericks. So you need those guys, but also those lovers. Lovers, we mean people who really care about something. Think about the do-it-yourselfers, the communities, the makers, the tinkerers, the enthusiast. This is an ornithologist, somebody who just watches birds for the sake of watching birds, for the joy of watching birds. There's no other intention, but there is something this is a role that's got to be occupied in a cycle in order to have like all the complete roles established to go through a cycle. The creator, the creative engineer, the scientist, the artist, the artisan, the designer. But you also need, in order for growth, fighters. What do we mean by fighters? The entrepreneur who wants who wants to destructurized, established markets. The athlete is also a representation of this energy that's required. The activist wants to change the status quo. The same with the rebel. What about a world without rebels and activists? Everything would be static and stuck. But then you come up to the top of the cycle, the ruler, the decision makers, the CEOs, the investors, but also the experts, the specialists who really know. They belong, of course, to this top position. And then you need the fool, the jester, those who are the ruler and the jester. What about an ecology without a jester? The entertainer is a variant of this archetype, the DJ. Well, you need DJs, that was like our. And you got the destroyer. The destroyer arises wherever it comes from. You have those figures in history, the disruptors, the reorganizers who say stop. Of course, the disruptive innovators, like the iPhone was, like for a lot of people. And it leaves behind a lot of orphans, orphan childs, people whose life gets destroyed, whose product gets destroyed. We talk so much about creative destruction. Isn't it funny? Creative seems nice, but what about the destruction part? Or what about this destructive creativity? Anyway, I just want to go into detail. I don't have time for that. I just want to, the frail. What about the frail? So many, you're in this stage of this cycle. And then you need like the caring person, the nurse, the healers, who to take up, the coaches who help you to overcome, to forget, but also the landlords. Without a landlord, where you can drink your beer and talk about all the things that went wrong in your life, how could be a cycle completed? The caretaker, who's like the handyman, excuse me, who's like, it's a handyman, it's not just a caretaker, who's like preparing the bulbs when they're gone. The cleaner, who's cleaning your office? Without a cleaner, no cycle. So the ecology, the role would not be so. And then you need like the visionary for the next steps, the prophets, the seers, those who kind of look into, of course, she's like a perfect seer because of her, also the blind seer, in this case, the autistic seer. Anyway, it's a mythological role almost, but she's an archetype. She's a realization of an archetype of a necessary, absolutely necessary role in this eco-cycle of innovation. The futurists, of course, we need them. And the role models, those who are pointing towards what would be possible. And then you need the sages, the philosophers, the spiritual leaders, and the mentors who help you through this passage. And eventually, one of my favorites is the dreamer. Why the dreamer? You would never ever start something new without naivety. You need the idealists. You have to become the child again, like in the Bible, so that you can start fresh. So what you see here is like all those roles and all those functional roles, they're archetypes. You gotta have them in your network in order to go through those cycles. And the cycles will come, the cycles are irregular, the cycles are like, as we've seen, like not so beautifully scripted like here. They are more ugly sometimes, but those roles are out there for a good reason, and they're survived the mythologies for a good reason, because they're linked with adaptive cycle. I truly believe that there is like a almost functional reason why they survived in our stories and why we find them everywhere. So what we did in the tobacco factory was, and here you see the director of the tobacco factory, Chris Miller, and myself, and we hosted workshops there with the tenants on this area. And we said, look, and you see this analysis of like autocatalytic cycles between the tenants. So we just asked them who in this area of the tobacco factory did something that helped you in order to do your own stuff, who's inspired you or supported your own. So, and we analyzed the changes of those autocatalytic cycles over years in order to look at how this whole ecology there emerged. With the members of the tobacco factory, we looked at who is missing, the missing link analysis, and we together with them. So it was a co-curated, community-curated search for the adjacent possible, or exploration of their adjacency grid, as I called it before. So where could we next? So who's missing? What could be like what we call like almost closed autocatalytic set? So whereas like this, if we would have this one more link, we would have a finished cycle. And from that, we have the missing links. Well, and what you see here is like, as I said, competing and completing roles. This is just like one example, because even there, it's always complex because the roles of those archetypes, and if they're competing or completing, is changes over the stages in the cycle. It's really horrible. You start with something and it always gets more and more complex, but that's how it is, right? So you don't have the same relationship between the ruler, for example, and the warrior. Here it's in this cycle from omega to alpha in the Bas-Holding cycle. It would be different from alpha to R. So just like I want to make it more complex, but you see here some analysis, and here's my romantic heart. Just like here, things really start to open up.
I'm sorry to interrupt you, but I don't know how much do you have, because the time is up. So.
Okay, no, it's not a lot. It's really just like 2 more slides, okay?
Okay, but the time is important.
I'm aware of that. I'm excusing myself already, but just like, let me just like share my romanticism here. What you see here is from all those roles, and it's the weighted degree. So it's like how much input they get from others and how much they catalyze others. It's the seeker. So those who are keeping, we talked about ontic openness before, right? So those who are keeping the system open are the ones with the highest importance in terms of role in this stage of the cycle. It's the seeker, it's the creator, it's the dreamer, So it's not, I'm talking about this stage where in the reorganization cycle, sure. But I just want to give you just like one last impression about the cycles that there's 9 2 or 3 ring cycles that we discovered here. And what you see here is like, you have one cycle that's linked with, I would say, like healing and reestablishing after breakdown. Here it's really about the visionary, the dreamer, the seeker, about figuring out what's next. And here is like a very dangerous cycle because it has a very high destructive power. It's like the orphan looks for the visionary, but the visionary can inspire the warrior, of course, yeah, who wants, so there's like the fanatic, who else? So that's why the destroyer is here. So I don't have time to go through it. It's just like one last thing, really one last thing. That every ecosystem has cross-scale structures and scale breaks. So we know that, right? Space-time, global, local, the mouse occupies different species, niches in time and space. But between those different scales, that's the problem. There's scale breaks. And this is why I'm bringing this up, because there's like a zone of challenge and opportunity. If you occupy that, there's a precariousness there. So everything that renews us, and you have in the course the centripetality, Ulanovitz centripetality course, and they suck up. We talked about centripetality and centrifugality. The centrifugality, they suck up from the periphery of the ecosystem people. And who is the periphery? The periphery is the orphan, is the seeker, is the dreamer, is the visionary. So we have in our innovation ecology multiple peripheries according to the scale we're looking at. I'm just bringing this up because the periphery is exactly what the scale breaks are. This is a completely different idea of what the periphery is in the network, because you have to understand what the scale breaks are. And that's where the new emerges. That's what we've learned from Elm and the late work from Halling. That's where the new comes from. And we have to activate and take care of our peripheries, of our multiple peripheries, of the seekers, the visionaries, the dreamers, and the orphans, because they are the ones who help us eke up a new niche space that's different than the old one. And yeah, that's where I gotta stop. Thank you very much for your attention.
Thank you very much to all the panelists. And I see 2 questions from the audience. One is for Simone Bastianoni, and it is about ecological footprint and the carbon footprint. It seems that ecological footprint is not a rigorous indicator, and it could be better to use a carbon footprint. So what is your opinion on this, and why, of course? Unmute yourself, please.
My opinion is that every approach has its shortcoming, for sure. Maybe ecological footprint is not as precise as, I mean, has more assumptions, let's say, also than other approaches. But there is a big but, because ecological footprint is the approach that is most understandable by the public. And so this is a very important feature in ecological footprint. That's why I think it's worth to work to make it better. it's not perfect for sure. I mean, no approach is perfect. And I agree with you, and I have same data that the correlation with carbon footprint is very high, also because carbon is the usually the top component. I mean, the most important component in the ecological footprint. So, but it shows something else than carbon footprint also. So I would say it depends on what you want to use the approach for.
Okay, thank you. And the other question is for Harald Katzmeier. He wrote, if it's possible to give us a case where you have met all or some of this, how did it work out? Or if you have experienced relation with all or some of this.
This is a very fair question. No, yes and no. So first of all, as I showed in this one competing and completing diagram, so there's really opposing forces, but through to this effect of indirect mutualism, everyone benefits because it's the pre-requirement to go through the cycle. So they're not there. You just. But what we did was like we brought people in a workshop setting in a room where we had most of those functional roles represented, and we used like the software to look at what should be done to improve the area, to make it more what's needed and so on. Yeah. So, and what we managed was like really to work on a map where people differ. So where you have a huge variation, like in answering this question, but also where is like a common ground. And the common ground eventually was, and this was like the huge step forward, that people started to understand why, and you have to imagine this area is really huge. It's really huge. So, and there's like high-tech companies having their offices there, and next to the high-tech companies, you would have like a place for homeless people, a place for unemployed repairing bicycles. Nobody understood why what I mean, this does not really makes it sexy to all those classical incubators where startups are cramped and etc. So it was and suddenly they realized the idea and the concept, and from there on it was much easier not to love or like the other, but to at least have the respect why the other is here. And I'm not talking about trust, I'm really talking about respect. So it's like it's work, and there is a community, and this is Chris Muller, it's his role. You need this person who really works the relationships, who really works the community, and the community can only be like and you have to hold all those contradictions and all the tensions. You have people in different stages of their business cycle. But the interesting thing is, talk about reinvention. When we did last in 2019, because we worked with them now for many years, and we were like, our philosophy was really applied from the beginning. Therefore, it's a beautiful business case that this can work. It can work. It can work. That to bring together this variety of roles, let them work and co-curate together who is missing, in order to create this culture and understanding of the variety of different roles. Because in the last time we did this, it was one third of the organizations there who said that they were like in the stage of reorganization and reinventing themselves. So they understood, so to speak, the necessity and the value of that are, if everyone would be like in the reorganization stage, we would have a problem. So it's beautiful to have like these people who are at the growth stage, who are like in the crisis, who are in the moment of starting from scratch, et cetera, et cetera. But you need community organization, community management, and you have to have a very, very the capacity to hold those cross pressures, how it is called, and this cognitive dissonance, which resolves absolutely at the higher scale. Because when you look at this, there's no cognitive dissonance. Everything falls beautiful at its place, and everyone has its role in the whole. But the whole is not a is in the stage of disequilibrium, of course. it's not a peaceful place. It's conflict, of course, friction.
Okay, thank you very much for the explanation. And I don't see any other questions. So if Valerie doesn't have any other question.
No, perfect.
I give the stage to Harald again to the closing remarks, since we are on the time of closing.
Well, so thank you very much. This was like a long afternoon. I think that it was a super interesting afternoon, at least for me. And I'm just not saying that. I mean, the thing is, I've listened to our. Some of us, we know each other for many years, and it's just beautiful to see how the work evolves. And sometimes it's so important to just hear it again, just like with other words, so to really digest it. And I'm very thankful for that. I just want to say one thing, and this is what motivates Brian and myself, and we will have another round of that. I strongly believe that the ecosystem sciences and ecosystem thinking in the broadest sense are absolutely core for not just understanding the world, but really come up with a new epistemology. We've talked about epistemologies, about intrinsic, implicit, the implicit order, the implicit world, right? Not just the explicit, to really integrate the implicit and overcome what Ika said, all those dualities. We need a new epistemology. I call it cosmology, but it doesn't matter. I mean the same, because our old cosmology just like creates not just havoc, but we are trapped. This is a dead end. This is not something, there's no happy end for that. This is not just like fatalistic, depressive thinking. I think it's very realistic. And when you think about not so much about, this is, I think, a very important distinction or almost a gap that we see today between people who are trying to figure out ways to avoid confronting themselves with the reality. And when I talk about reality, I mean the outer and the inner reality, okay? We try to avoid to see try to see and sense what's going on the inside and on the outside. And then there's those who are bold enough to look at the outer and the inner ecologies, the sciences and the wisdom and the knowledge that you represent are absolutely key. And I don't say because it's the bridge between the natural sciences and the humanities. It's ecology. It's the bridge. It's the bridge. Also to psychology, and we need this horizontal, lateral thinking more than ever. And it's just the question. I mean, there's so many treasures that are trapped in your malls, and they're not known, or as Bob said before, if you would say this when you're at an examiner, don't say it, because so this is now it's the time to share the story and to promote those stories. And Brian, I'm looking to you. I mean, we will try to do our best and keep on organizing those settings. Hopefully next time we'll, in real person. Yeah, there's a strong need for this new, different thinking, and the prism that we look at the world has got to be changed to see things that are unseen at this moment. So, Brian, do you want to also say something at the end? I think you started, and maybe you have also like some closing.
Thanks. No, you said it all very well. I would just add two things. Maybe one is that the themes that seemed to be throughout here was the trade-offs message. So whenever you try to do too much of one thing, you're probably going to make a mistake. And we saw that in so many talks about it's not maximizing something, it's finding the balance between whatever dimensions and variables you're looking at. Did you want to say something?
Yeah, sure. I mean, this is the ambiguity story, right? It's both ways. It's always both. But I think I just like I just would underline that a way to overcome this kind of either or thing is to really think strongly and focus on the cycle, because every stage has its own. There's like this correlate thing. Every stage, there's a time for this and a time for that. There's a time for maximizing, because you can tell a 20-year-old woman or man don't maximize. Of course, they try to maximize. That's for the stage, the way to do. But if you do it your whole life, then something is wrong. So I just want to say, it's like maybe we can have like, because to find this optimum, this optimum itself is moving, and just
right. No, and I think that, and Joao mentioned well about the, and Simona talking about GDP as being always the maximizing variable. And one of my mantras recently has become, if you're just anti-growth, that looks wrong too. And so I say, well, there's a time to grow. It's just not always.
Yeah.
And so, get that across. But I think the second message was about, back to Ika's talk at the beginning, with transformations, and ending with your rebels and your, your seers and that. So it is time to maybe put those answers down on our exams and teach our students to be the rebels and make that transformative change that we need. So, yeah. And thank you, FAS, for organizing all of this workshop, and for all the speakers and everybody here today. Really appreciate seeing you.
Thanks, Valerie. It was your work.
Thanks to everyone. And I would say, before we go home or change rooms, I just wanted to add that the presentation, the videos will be uploaded on the YASA website as well as on the FS Research website, and you will receive the links. Thank you again for joining today, and have a good evening. Bye.
Thanks. Bye.
Bye, everybody. It was a pleasure.
Yeah, it was a pleasure. It reminds me that all the most interesting work I've done is with this group. So thanks for that. Next time in Mern, maybe.
Virtually,
next time wherever. Okay.
Take care.
But
take care, yeah.
Somewhere.
There's still a virus going on.
Or samewhere.
Yeah. All right. Bye now.
Stay healthy and safe. Bye-bye.
Ciao.
Bye.